Like we want to make biology and medicine be almost as much as technology as possible, because no one doubts that computers get faster every year and components get cheaper every year. And so no one doubts that, right? That's very visible to the naked eye. So why can't biology be exponential like that?
Forever young, I want to be forever young.
Today's June 24th, 2020. I'm Brent, Nally, and I'm here with a very fascinating stem cell expert, Dr. Leonardo Ferreira. And Leo is what he likes to go by, is a PhD in cellular and molecular biology from Harvard. And Leo has been at UCSF as a postdoctoral scholar since June 2016. And also, Leo is the founder and chief scientific officer of Immunodietica. So, Leo, welcome.
Hi, thanks for having me.
Definitely. And you're here from your home, which is right across the street from UCSF in San Francisco. Is that right?
That's correct. Never too far from lab.
All right. Awesome. So before we jump into all the fun things we're going to talk about stem cells and gene therapy and how we could potentially solve the human aging problem that's, currently killing about 110,000 people every single day, the largest problem on the planet by far. Let's talk about who you are and how you got interested in this world of regenerative medicine and stem cells and gene therapy. So the floor is yours. Just love to hear a little bit about your background, and maybe you can share also like when you started thinking about maybe curing aging and being a doctor and being a molecular cellular biologist to help us solve this problem.
Yeah, so, I think it all started in Portugal, where I'm from, when I was a little kid. I used to play soccer every day, and you always hurt yourself, or almost always, at least I did anyway. And so I remember being interested in like how you have a wound, and then it gets healed, it regenerates itself. And so that's always interested me. And so I always also during war, like soldiers, they get injured with bullets and all kinds of stuff, and then they can heal many times. Or sometimes, if you lose a limb, it doesn't grow back. But if you look at like a salamander, it's got like bone and flesh and skin just like we do. But if you chop its arm, it grows back. And there's some creatures that are even crazier. Like there's this planaria, it's like this flatworm. If you chop its head, the head grows back, which maybe it might be too extreme to apply to humans. But so I think all that stuff was always in my head, growing up and through middle school, high school. And then when it was time for college, I studied biochemistry. But I just felt like if I understood the molecules that make us, we could get some control over us. And even like in college, when I was a freshman, I remember being in a library in college. This was back in Portugal, University of Coimbra, a very old place, almost 800 years old. And so I grabbed this like genetic engineering book, not because I understood much of it, but I liked the engineering part of it. Like you're engineering genetics, which is what we're made of, the DNA, the genes that made it. And so I think in general, throughout my whole life, I always thought, life is very interesting. Can we understand it better, and can we control it? Can I one day, if I cut my finger, can I grow it back? Can my wounds heal faster? Can I, instead of getting older, stay the same or even become younger? Because in the end, it's all cells and tissues. There must be a way to convince cells to do what we want them to do. It could be expressing things, like for insulin production. We're able to convince cells to make things for us. Like many molecules that are now sold as drugs, cells are making them. So can I likewise, make stuff for ourselves that will make us younger, will make us healthier, will make us stronger, will make us smarter? I mean, that would really be the idea.
That's awesome. And yeah, planarian flatworms you mentioned, I believe if you cut a planarian flatworm into 276 different pieces, it will be 276 planarian flatworms. And, you mentioned that species. There's also Hydra that doesn't appear to age at all. So it's scientifically termed as biologically immortal. And one thing I like to share with people is that, we have our somatic cells, which make up the majority of our cells in our human body, about 99%. But we have our germ cells, our reproductive cells, the sperm and the egg, which are also scientifically termed as biologically immortal. So they just don't age. I personally think that they age just a little bit. It's just basically negligible compared to, our somatic cells, which kill us from aging so much that it doesn't even matter. So really interesting stuff. And Leo, what really like drives you at this point? You're working at UCSF, and I introduced you with you founded a company as well too. We can get into more details about both those, but what's really the driving force of your research? Like, what are you really trying to accomplish, not only for yourself or maybe your friends and family, but for the greater world?
Yeah, so I think, I just like to see the body as like an organic machine made of cells and tissues and organs. And I always like to think that, if you have an old car and you keep replacing the parts in that car, you can have an old car forever. You can have like a classic Porsche or Ferrari for centuries, right? And so why can't we do the same with people? I feel like so much technological advance has happened, in the 20th century. I think 21st century, I'm hoping, is a century for biology. We can do with cells and tissues what we've been doing with a chip for computers, what we've been doing, internet and all that. And so more specifically, I've been working on organ transplant and immune tolerance, I guess, for almost 10 years now. So when I was in college back in Portugal, almost all journals are American, and so many authors. So it's like, maybe I should go to America myself. Maybe that's where the action is at. And so I remember there's this thing like Time magazine, this cover that said, "Stem cells will save your life." And so I think ever since, I have it somewhere in my home office, is like many like handwritten notes that I took about all papers about stem cells. Could be embryonic stem cells, could be adult stem cells, could be reprogramming, right? A process by which you take an adult skin cell or blood cell back, you revert the clock to become a pluripotent stem cell-like cell. And so I read a lot about this, and just, again, trying to control cell fates, what cells do, how they behave, and, not just cell level, also at the organism level. And so at the organism level, that's where immunology came into play. So for graduate school, for my PhD, I worked with Jack Strominger, who is now 94 years old, and Chad Cowan. And so I worked on organ transplant tolerance, immune tolerance. And there I focused on the graft, on the organ. So you could imagine engineering the organ such that it's compatible with everyone from the immune perspective. So there's these molecules called HLA on the surface of cells, and that's how the immune system can tell self from non-self. And so I focused on that a lot. And actually, we've been able to develop a first step towards a universal stem cell. So you could imagine making organs. You could 3D print organs from these universal stem cells, and I can just go on Amazon Prime or any other vending service you like and just get them to you, the right measures, the right shape, given to you, and again, comparable with everyone. And now for the past 4 years since I've been at UCSF, I still focus on immune tolerance, but now not from the organ side of things, but from the immune system side of things. We've gotten very good at engineering blood cells. Like, blood is liquid, everyone can give you some blood. We can grow blood cells, we can purify with many markers like barcodes, if you will, and we can genetically modify them. And so I've been working on this group of cells called regulatory T cells. Most T cells, they kill stuff. They kill cancers, they kill virally infected cells. They can even kill your own cells if it's an autoimmune disease. That's not good, though. But then you have this small subset that kind of keeps them on track. That's the regulatory T cell. It's like the general of the army. Nothing goes overboard if the regulatory T cell is working. And so I've been working on an engineering dose. I can change their specificity so I can use them again to kind of democratize the transplant of tissue. So regenerative medicine, will only happen if you can actually put cells into people, right? So not just getting a stem cell to become a heart cell, a muscle cell, a skin cell, a neuron, but also actually putting that cell that we made into people. And so the immune barrier, I guess, is what really I've been focusing on for the past decade.
Okay, super cool. Now, you mentioned HLA there. That stands for human leukocyte antigen. And, me personally, Leo, I think you know this. I went down to Mexico in December of 2018 to a clinic called Dream Body Clinic, and I had mesenchymal or mesenchymal stem cells. Dr. Arnold Kaplan, who named them that in the late 80s, has rebranded them to medicinal signaling cells to keep that MSC name there. And what I have been told by the many different stem cell experts is that the stem cells that I received, which were from the Wharton's jelly, a specific part of the umbilical cord from a healthy human birth from just a few days earlier. Healthy just means virus-free and all that. But what I've been told by many sources is that the MSCs from that umbilical cord, because they're so young, they call them day zero, they haven't developed yet that HLA, which, as you already stated, is what tells the immune system that, hey, this is a foreign cell, we should attack it. So my question is for you, first of all, I really think it's smart what you guys are doing and what your research is doing to have a universal, I think is the word that you use, a universal stem cell that can work for everybody and not have that HLA problem. But my question is, we already seem to have this, right, with the Wharton's jelly, no HLA, no problem. And they seem to be in a lot of abundance. There's still many, many babies being born all the time. So what's wrong with doing what I did, or why is your way better, I think is a better way to think about it.
Well, I think it's our complementary approaches. So the mesenchymal stem cell, I mean, it's very interesting cells. They seem to be found in several tissues. And of course, the younger, the better. Because again, it's said, like, in terms of like the maturity of the antigenic display that they have. But the thing is that, stem cells come in many flavors. And so I mentioned at the beginning, like, we all come from one cell. So that one cell is kind from 0 to 10 is like 10 in terms of potency scale, right? Because that cell can give rise to a whole human being. And then when you go down the line, you can go down to like, blood cells, blood stem cells, hematopoietic stem cells, HSCs, which are the active ingredients of bone marrow transplant. So by the way, if someone tells you there's no approved stem cell transplants, that's not true, because bone marrow transplant has been approved for decades.
Exactly.
Right? So stem cells have been around for decades. And actually, blood stem cells were the first ones to be discovered in Canada by McCulloch and Till. But so that's as an example. So blood stem cells, so far it seems that they can give rise to all cell types in your blood. A T cell, a B cell, a macrophage, a neutrophil. But they want, or, there are some reports, but not really clear, that they'll give rise to a muscle cell or a skin cell or a neuron. So for that, for neurons, you need a neural stem cell. For muscle, you need a satellite cell, which is a muscle stem cell. So you go all the way from making all cell types in your body, and that actually is also true for the embryonic stem cell. So if you have the blastocyst and you have the inner cell mass, you can then take from that inner cell mass the embryonic stem cell, which are pluripotent. They can give rise to all cell types in your body. And so from there, it can go all the way down to unipotent. So like a muscle stem cell only gives rise to muscle. And so I can't use it to generate new, cardiomyocytes or to generate new skin. And so likewise, the mesenchymal stem cell, traditionally, can give rise to 3 cell types. Can give rise to fat, to bone, and to cartilage. I personally have used mesenchymal stem cells to give rise to fat. Because in my PhD lab, some of the focus was in metabolic disease, modeling using stem cells. You can imagine, you can do like, you can have a population study, but in a laboratory, where you take cells from different people, you make into iPS cells, which are these pluripotent stem cells, and then they have different mutations, right, that these people have, and then you can differentiate them into bone, into cartilage, into fat. You can even take them into like endothelial cells. And so that's the potential. So now, of course, 2 things. One is that sometimes you don't need the cells themselves, you need the signals that they release. So, when you say that someone's trying to rebrand them as medicinal signal cells, I think it makes sense, right? Because sometimes it could be that these cells are making cytokines, are making growth factors, are making immunomodulatory molecules, which is their job. You don't want them to become tissue, you want them to just deliver these goodies. So I think actually blood in general is an untapped resource, because blood goes all the way from your brain to your tippy toes. And so if we can use blood cells or cells in general, not just to make new tissue that is degenerating, but just as carriers. Like, I want to deliver a certain molecule to a very precise location. If I take a pill or if I inject something, it goes everywhere. But if you have a cell, even a blood cell, the blood cell will go everywhere, but I can give it a zip code, right? Because there's chemokines and chemokine receptors that can tell it where to go, right? So a cell can be programmed to such a more complex extent that it can make the cell go where you want, when you want, and do what you want. And so in any case, so just say, so mesenchymal stem cells have a limited potential of differentiation compared to an embryonic stem cell. Like a bona fide embryonic stem cell, I can make all 3 germ layers. And so again, you can have diseases that need cell types from each one of these layers. And so for that, the ideal, and this was actually proposed by Yamanaka himself. So Yamanaka was a scientist that came up with reprogramming. So from his view of the world, you would think, well, we don't need embryonic stem cells anymore, right? Because you just make your own embryonic-like stem cells. But even he recognizes that iPS cell technology is not perfect yet. There's variation. It takes months. It costs tens of thousands of dollars. And sometimes cells have what's called an epigenetic memory, meaning that they remember what they used to be. So like an iPS cell that came from a skin cell is more likely to be differentiated into a skin cell than into a cardiomyocyte. And so that will be a problem, right? Because you wanted this process to be efficient. And so to end that, to say that one idea would be to have a centralized bank of frozen, cryopreserved embryonic stem cells, pluripotent stem cells, which then they could be ideally universally compatible. So you have this stem cell line, this universal stem cell, that is very good at making cardiomyocytes. I don't know why. That person's genome just gives rise to amazing cardiomyocytes, or to amazing skin, or to amazing dopaminergic neurons. But once you capture that potential, you can now make it available to everyone. So now everyone who needs a cardiomyocyte can use cells from that master cell line. And so that's universal. That's why embryonic stem cells still have a place, and universal ones more so than others, versus other types of stem cells that have therapeutic benefit, but they might not give rise to all the tissues that you might need to replace during disease.
Okay. Very in-depth answer, and I really appreciate that. So I guess just selfishly, it leads me to my next question. A little over a year ago, in March of 2019, my wife and I decided to go through a company called Ferreira Labs. I actually have their water bottle here. I have to scoot back at the digital background. And my wife and I had our bone marrow frozen through Ferreira Labs. They're a company based in Michigan. I think it's cryogenically being stored in a partner company of theirs, which is in Indiana. We went to Orinda, California, which is just east of Berkeley, California. About an hour drive from us. We were in Woodside, California. And we went to Dr. Chad Rogger's office. You can check up, I'll put a card right above if you guys want to watch this video to see my wife and I actually have this done, and we interviewed Dr. Chad Rogger beforehand. So I did a lot of research on this before I did it, and I wasn't convinced at the time that I'll ever actually use this for anything. And it was more of an insurance policy for my wife and I. But the risk that, I thought about and I did a lot of research on and consulted a lot of, what I perceive to be really intelligent people was, hey, was I potentially doing harm for my wife and I, extracting all of this bone marrow blood that potentially my body could need? So what do you think about what my wife and I did? Was that smart? Is it too unclear right now to know and to see how this, technology that people like you are working on will play out? What do you think about what we did there?
Well, I personally think it's a good idea, if for nothing else, in the sense of, like an insurance policy. I think you put it best, because hopefully you won't need these cells, at least for some disease. But if you do need them, it's good, very good to have them. There's many blood cancers that the treatment for them is a bone marrow transfer, a bone marrow transplant, right? And so now, because of these HLA molecules, I should say that they're very diverse. Like, we're all different. HLA-A, there's 2,000 alleles of it, 2,000 flavors. It's more than Baskin Robbins, and so you can just imagine that. And you have 18 of those, because if HLA-A, B, and C, then eventually DR, DQ, and DP, and then the class 2 HLAs, which are DR, DP, and DQ, they have 2 chains, alpha and beta. So it comes down to 18. So you have 18 alleles, 9 from mom, 9 from dad. And so if you do the statistics, it's almost impossible to have 2 people in the world that have the same exact, set of those 18 genes. And so because of that, if you need a bone marrow transplant, it would be best to be your own, right? So if you store your young HSCs, and I say young because it's been shown that HSCs do age, unlike, I guess, embryonic stem cells. they seem to have this thing where so HSCs they can give rise to all cell types in your blood, but they do so with different frequencies. And so what seems to happen is that over time with aging, there's the obvious thing, which is it'll accumulate DNA damage, right? I mean, physics still exists, like sun, so UV radiation, chemicals, the food that you eat, all that is happening regardless of what we do. And on top of that, the cells themselves, they seem to have over age, they have like a myeloid bias. So immune cells, blood cells have lymphoid and myeloid. Myeloid are macrophages, dendritic cells. And lymphoid are B cells and T cells. And so over time with age, your HSCs make less of the B and T cells, which are the adaptive immune system that fights infections and cancers, and make more of the myeloid cells, which are important, that they communicate between innate and adaptive, but still. So you could imagine that you have an aged HSC that makes less of those, good T cells and good B cells to keep you protected. And so, actually immune senescence is an up-and-coming topic because, again, like old patients versus young patients and in general. So again, me personally, I think it's a good idea to store your HSCs at their youngest possible age. And that's why, again, some people, when they have a baby, they store their babies, right? HSCs, umbilical cord, for the same reason, because if that person, if a leukemia or something like that, they would need a bone marrow transplant. If it's your own, it's the best possible scenario, because I should say, if not, if there is too much of a mismatch between the donor and the recipient, there's this terrible disease called graft versus host disease. Yeah. Where so usually, from even most of my work, it's always the recipient attacking the donor material, right? Like you put in a kidney or a liver, and then he gets attacked. The graft versus host, the tables turn. Now it's the donor's cells that are killing you from the inside. And so it's a very sad and very tragic disease. And so the best way to avoid it is just to have matched cells. Now, of course, with universal embryonic stem cells, you could make your own HSCs. But we're not there yet. We don't know all the secrets, all the secret sauce, if you will, to make, bona fide, long-term, young HSC all the way up from an embryonic stem cell. And so as far as blood is concerned, most therapies and most research is done with blood cells and not with embryonic stem cells, which then become blood cells. It's also very inefficient from my personal experience. If to make embryonic stem cells into blood cells, you can throw a lot of cytokines. It's a mix of voodoo and biology, if you ask me. But, you can convince them to become this tissue, embryonic tissue called a mangioblast. So blood is mesoderm, and so are these endothelial cells. And so you have this really cool thing in a dish, it's like a Frankenstein thing going on, where you have this layer of cells in your petri dish, which then start popping out, blood cells. And then you collect those cells in your supernatant, and then you can purify them using flow cytometry assisted sorting. But anyway, long story short, we're not there yet, making good HSCs from embryonic stem cells. So it's best to bank them, and so so you also can use your own.
So how far do you think we are? Best guess on how far we are to managing this technology at the level where it's actually useful for humans.
To generate HSCs from stem cells, from embryonic stem cells?
Yeah, basically to use it as a treatment, right? So that it can we can inject it into people in a safe way, and it can actually be beneficial to help them fight diseases and maybe even reverse aging.
I think it'll be at least 10 years, maybe even 20. There's a number of things why. So, science itself, can be slow, can be fast, can be in between. And then the other thing is also the trial part of it, right? So when it involves people, it takes exponentially longer. And so one thing will be like, you have to work in mice. Our favorite animal in biology seems to be the mouse. And so that's one thing. The other thing is to actually do this in people, right? So then there's more restrictions. It takes longer. But, we've known a lot. I should say, so the blood is a great system because we just have this, immense catalog. Like any blood cell type you want almost, you can purify it in a tube. And that's very powerful because now let's say I want to study, Th17 cell. It's a T cell, it's CD4 positive, it's CD3 positive, it's, has this factor X, Y, and Z. So, so you can have all these logical gates, if you will, and you can purify the exact cell that we want. And so in that sense, we're very good at that, at purifying existing cells. Now making new cells is a different story. And so again, I think the HSC we're still understanding what HSCs are. Like, how do you get a pure HSC from a person, right? Because how do you know how good you did if you don't have the answer sheets, right? So we're still, so we're still working on the answer sheets, so we can know how can we get the answer. The same is true actually for the cells I work with, the regulatory T cells. We're still figuring out what the answer sheet is. We know maybe 2-3 genes that should be there, but how about other genes? And I think, and not something that I'm working on actively, but like I think AI and all these sorts of stuff, I think will actually be a major help, because our brain just cannot comprehend having 22,000 genes going up and down to different levels in like different cell types and different cell trajectories. So we need some more powerful analytical tools to really, boil this down to something that we can do in the lab. So yeah, so I think 10, 20 years till we can really, like, you go to your doctor and you get this.
All right, so if it's 10 to 20 years until the work that you and your team and other stem cell biologists around the world are working on, where it can actually really dramatically help people, then what can people do right now if they want to use stem cell technology? And that could be anything. So we'll also talk about exosomes either now or sometime later, which are secreted from stem cells and other cells. What can people do right now if they are in pain and they want to, get the best benefits from stem cells, regardless? Let's say that they have the financial means to do so and they just want to get better. What's your advice on where do they start? Who do they listen to? Because it's a crazy world out there. There's people like me on the internet making YouTube videos, but I don't have a degree. I'm just trying to help and contribute. There are really brilliant people. There's, charlatans and things like that. So how do you find good information? What do you do if you want to learn about stem cells and you want to improve your health?
Yeah, it's a very complex landscape out there, that's for sure. Sometimes, maybe, I don't know if you say in English, but we say where I'm from that it's half the world, trying to fool the other half. Sometimes it feels like that. But, so two things, I guess. There's definitely many bad actors out there, and that's what gives you some, like, horror stories even about, stem cell clinics, stem cell tourism. But then, stem cells, they're here to stay. And as I mentioned, blood stem cells, they've been used for decades, and, they saved many lives, and we know pretty well what they are and how to obtain them. So it could be straight from the bone marrow, like yourself did. There's also, I worked with a lot doing my PhD, which is to use mobilized peripheral blood. So there are some drugs that if you take them, they call your HSCs into your blood. So when you collect your peripheral blood, it's going to be enriched by blood stem cells that would otherwise just be residing in the bone marrow. Like, whether that has some side effects or not for the person is a different story. But from the point of time of, like, collecting the cells, it's more convenient, obviously, to just have an IV to collect blood and go with a bigger needle to the bone marrow for a biopsy. And so we have that. And so, but now this paradigm has to apply to other stem cells also. Mesenchymal stem cells, as I mentioned, that could have multiple benefits, could be different types of tissue. Could be even factors that they secrete. This is a lot of research. I used to go almost every year to the ISSCR, which is the International Society for Stem Cell Research, and that's where really academia and industry come together. It's actually happening right now. It's virtual this year. Unfortunately, but so, and you go and you see a lot of research on mesenchymal stem cells, and it's presented at these conferences every year. Obtained from different tissues for different models of disease, both in animals and in humans. And then, of course, you also have the whole, organ printing, right? You have embryonic stem cells, which you can make different cell types, and then you can have a scaffold. So I think it was in Israel that a group succeeded to print like a small, but like 3D heart that could actually pump. And so this is the beginning, right? So, and then if you go here in the US, there's the Wistar Institute that has like a trachea, and like you can go on their website, there's many examples of organs being built. It usually follows the formula where you have a scaffold, so you have an extracellular matrix that gives a shape, and then you seed it with cells that will then become different types of cells. So for people, I think the best, like the NIH has information about this, and the universities as well. And then from the clinical side, you have that doctors who want the best for their patients. Like doctors have conferences, our own for scientists and also just for doctors. And so that's where a lot of knowledge is exchanged, is really in conferences, because maybe, before something gets published, which could be 2 years from now, you can hear it today. And 2 years makes a big difference in someone's life, right? If we talk about individual lives, I mean, you could benefit from a treatment today, not 2 years from now. And so I think conferences, which I hope go back offline soon enough after the, I think these are, places where people really can learn a lot about these things. And then in general, I think also the accreditation, there's clinical trials ongoing. And then, there's two things. I guess the short answer, if you want to get the most benefit from stem cells, you should go to, you could try visiting Japan, because Japan is actually at the forefront of stem cell trials. So they were the first to use stem cells to treat macular degeneration, so the generation of the eye. So they generated their stem cells. They generated RPE, which are retinal pigmented epithelial cells, and they injected them into different patients. And these were not even matched cells, because so the eye is an immunoprivileged site. So the theory there is that if you transplant cells into such sites, they will not suffer immune rejection. So even if these cells are derived from someone else's cells, that will not cause trouble. So that's ongoing in Japan. Also for heart disease. So that's going as well. And then also for neurodegeneration. So probably the hardest organ you can think about is the brain. But even the brain, there is stem cell-based strategies for it. So in Japan, they're also starting a trial where they're going to inject stem cells into the brain that will then differentiate in the proper environment into dopaminergic neurons. And so there you can have different options. You could inject iPS cells, which, you could imagine it could be a bit dangerous because, iPS, ES cells, it can become all cell types. So you could form a tumor. There's a type of tumor called a teratoma. So if you have a pluripotent stem cell, and you do this in mice, if you inject a human embryonic stem cell into an immunodeficient mouse, so a mouse that doesn't have an immune system to defend itself, it will form a tumor, a teratoma. And this teratoma is like skin cells, it has nails and hairs, it has everything. It's just the cells confused and just proliferating. You can also inject neural stem cells. So the brain has its own stem cell itself. And actually, even as adults, it's hotly debated, but we think there is neurogenesis. So new neurons are formed even as adults, in the hippocampus especially, for memory formation. And so, again, like no organ is immune to the benefits of stem cells. And so Japan seems to be at the forefront of that, of doing trials with different stem cell modalities. And then, of course, in the US as well, trials are getting started. It was kind of a sad story, but I think it's called Regeneron. It had a trial for spinal cord injury therapy with stem cells. And, this was maybe a decade ago. I don't even think I live in this country yet, the United States. And so I think they went through the whole thing, and there's a lot of promise and a lot of work where, even in mice, you sever their spine, and then you give this therapy, and the mice would walk again. I mean, what's more magical than that? Those that are, ridden to a chair can walk again. And so it was all in place, but then I think due to regulation, they ended up not going through with it. And they fill a lot of paperwork. And so I think regulation, so there's non-scientific reasons why this has been taking so long. It seems that, there's also regulation that also poses a problem. So this is kind of a double-edged sword. Like, those in charge might think, well, if you make very heavy regulation, then we have only the most absolutely safe therapy out there. But then the downside is that people will go elsewhere. And so it's a bit like abortion almost. It's a sensitive topic, but you could imagine that abortion is legal in some states, illegal in others, but it still happens. And so if it does, you might as well make it as safe as possible. Have as many professionals trained as possible. People even people like psychologists, like the whole team. There should be whole teams of people involved in this decision and this procedure. And so by not making it open and legal, you're just making things worse. And so I think with stem cell therapies, I'd rather see efforts like in Japan to expedite the review, to look at it, to really make it a priority, versus trying to, if anything, make it like in the current administration, they literally blocked fetal tissue research with federal funding. Like, we still do it because we have private funding, but I mean, you need fetal tissue for everything. Very diverse topics. So before aging and stem cell, that's an obvious one. But even for less obvious stuff, for like HIV, for example, you can't study HIV to its full extent without fetal tissue. Why? Because HIV does not infect mouse cells. It only infects human cells. So what we do is we can make a mouse that is humanized by using fetal tissue. For human fetal tissue, it can be used to make a mouse that has a human immune system of sorts. And now we can test vaccines and treatments for HIV in the mice. We could also try it out in people, but I think people would feel safer if it was tried in animals before. So it's almost as if by blocking fetal tissue research or federal funded, let's be more precise, fetal tissue, you're damaging people's chance of getting this new therapy, and or you actually, almost you're going to have to use people instead of animals, which should not be the goal. The goal should be try things in animals before using in people. And so you're basically endangering the living to have some sort of protection of the non-living, which again is not how it works, because all fetal tissue is from discarded material. There's very little, in my opinion, ethical problem there, because these are things that already happen anyway. If anything, it's ethically incorrect not to use it, because its material is going to waste. It's precious tissue that could be used for research and is not, because of a regulation. And so, so I think in general, where to go, I don't have a definitive answer. I spend most of my time in the lab anyway. But it seems like Japan is at the forefront of the, clinical trials for stem cells. And then I hope that in the US also starts catching up, because again, stem cells are here to stay, and there's so much data supporting different things to be done that it just has to be tested and trial.
So you mentioned pluripotent stem cells. Now, in October at RADFest, the Revolution Against Aging and Death festival that I went to, I interviewed Dr. Denise Renson, who is a naturopathic doctor currently working on getting her PhD. She might already have it at this point. This was October 2019, and she had just become the medical director of a company in Baja Cabo, Mexico, called STEM Aid, and they use pluripotent stem cells, and they say that they're having great results there. You mentioned that if you inject pluripotent stem cells into an immunocompromised mouse, that it will form teratomas, tumors, and this has been well understood. But what Dr. Denise Renson and STEM Aid state is that if you inject their pluripotent stem cells into healthy people, that they actually get really good results. Now, what they do is they make sure that they don't do too much too fast. So they say that they do about 25 million per day, and then the body naturally flushes those out. Whereas, I had about 300 million mesenchymal stem cells injected all throughout my body in one day at Dream Body Clinic, also in Mexico, in Nuevo Verde, Mexico. And I had no side effects personally. I didn't have any pain or anything. It's all documented. You can watch it on this card above here, all of my injections and process, and then I did follow-up videos on that. But my question to you is, Leo, this is a really crazy world that we're in, but we have the internet. It's 2020. We have the internet. We have all these forms of communication. But what I've found in my stem cell research is that most people just say that pluripotent stem cells, cause tumors, kind of like end of story. They're dangerous. But then I have this company called STEM Aid with this lady, Dr. Denise Renson, who I actually respect, and I think she's intelligent, and I think she's ethical. I don't think it's like a scam. It could be, but I don't think that it is. And they say that they are injecting, about 25 million a day. And what they do, I guess what's difficult is they want you there for 2, 3, or 4 weeks, getting injections every single day, because they can only do about 25 million a day. So it's this whole, it's in Cabo, Baja, Mexico. It's a beautiful resort. They're feeding you organic foods. You can get massages. It's like a resort. It's an experience, but how many people can take 2 weeks, 3 weeks, 4 weeks off work to go there and do that? It's a certain class of people who have the money and the financial means to do so. But it's controversial. So I'd love your, opinion on, I don't know if you've heard of STEM Aid, are there other companies like this doing this throughout the world? How do you, as just an individual sitting at home, maybe watching this on YouTube, how do you know who's telling the truth, who's not? It's a crazy world out there. So the floor is yours to kind of tackle this question in any way you'd like.
No, it's not easy. I mean, I was watching, I think it was a TED Talk the other day, and so they were saying they asked people how do they find out about scientific discoveries. And there's many ways. It could be on TV, on YouTube, on the newspaper, in comic books, through scientists who actually make them. And I think scientists came number 9 or 10. And so what that means is that most people will not hear from scientists about science. They will hear non-scientists about science, which is good and bad. I mean, I guess in one hand, you could imagine that, like scientists, their duty is to do science, and as scientists can only do so many jobs. But at the same time, I think if nothing else, telling taxpayers what their tax dollars went into for research, I think it's almost a duty at the same time. And so I think as scientists, we have responsibility to improve that statistic. And so being number 9, maybe make it top 5 next time,
I'm trying to make you guys number 1. I mean, that's what I'm trying to do. I'm trying to actually interview the scientists, like yourself, and hopefully give you guys more of a voice. And, now's the best time to plug Leo. You have a YouTube channel. Check the description below, everybody. Follow Leo on all social media, Facebook, LinkedIn, Instagram, Twitter. Subscribe to his YouTube channel. I'll have links below. Learn from the scientists. That's what I'm personally trying to do. I'm trying to interview these folks, find out the truth. If you're not already subscribed to my channel, subscribe, click the notification bell, select all notifications. That's really important for the YouTube algorithms to do that. So Leo, tell your audience that as well too. It's really important for the algorithms, how it works on YouTube, to select that bell and then click all notifications. And that way we're telling YouTube as well too that, hey, we want this stem cell technology immediately. Tell the YouTube algorithms that, tell all the social media algorithms this, because they don't work if we don't use them, these algorithms. So yeah, that's what I'm trying to do. I'm trying to, figure out the truth, because I didn't go the PhD biology route, like you did. I personally got a corporate communications degree, went to Silicon Valley, but I've been really interested in this stuff for a long time, 15 years or so. And I find that there's still a huge gap, even within really intelligent people in the scientific community, the experts on what's true and what's not, kind of as I just brought up with STEMaid. So I guess, can you maybe address, STEMaid, is it possible that they're doing what they say that they're doing, and it's just not it's not well communicated within academia, that this is possible, or what's possible?
Yeah, I mean, I think there's a couple points there. So one thing I should say is that, for example, for doing my PhD, I focus on immune tolerance, and I actually studied the most dramatic example of immune tolerance, which is pregnancy. During pregnancy, the mom is, as a fetus inside her for 9 months, and his fetus is 50% different from her, right? Because there's antigens from the dad. It doesn't get rejected, so we know that it is possible that the body, does not reject a foreign body if this foreign body has some trick up its sleeve.
This is what I tell people all the time. People were so worried about what I did in Mexico, and I'm like, well, look at pregnancy, and then look at surrogates too. I have a good friend who's over 40 years old. His mother, who he calls his mother, is actually his aunt. And his aunt, who he calls his aunt, is actually his mother. So, yeah, we've been doing this stuff for quite a while now. And, he's 40 years old. He's healthy. He's 40. He made it to 40, so he's that healthy. We'll see how long he lives, and I'm sure he's going to live a long time. So, in any event, yeah, please continue.
Yeah, no, so just say so the body, there are ways to induce immune tolerance to, could be to a graft, to the baby. And so that's one thing. Yeah, the other thing is that I guess, I think we mentioned that mesenchymal stem cells might be immunologically immature, right? Their HLA levels are too low to be cut on. And then also I should say that, T cells in the immune system, of the adaptive immune system, in order for them to kill, they need 2 signals. Signal 1 is the recognition of the HLA with the peptide, so the ID card. So they have to see the ID card. But then signal 2 is co-stimulation, is danger. So if there is no danger, the T cell does not attack. And so you can imagine a scenario where actually the opposite happens, which is the T cell becomes anergic, stops dividing, stops worrying about it. And so you can imagine a scenario where we have cells that, they have these foreign peptides, these foreign IDs, but because they're not dangerous, they don't cause inflammation. Nothing messes with them. And so you can imagine a scenario of cells that have low HLA levels plus no inflammatory properties. And so that those 2 things combined make for the fact that they don't get rejected right away by the immune system. And then in terms of tumor formation, Yes.
Sorry, you're referring to MSCs there from umbilical cord, right? Not like autologous MSC, not like MSCs from like an adult, right? You were referring to ones from an umbilical cord or from a young, placenta, something like that, right?
Right. So the younger the has the lower HLA levels. Yes. So this is being mapped out.
Just wanted to be clear for the audience. I
Yeah.
thought that's what you meant, but just wanted to be clear. Please continue.
Yeah, so that's one thing to take into account, right? Is that if injected cells somehow don't induce inflammation, and that's already halfway there for a bad immune response not to happen, right? And then in addition to that, I guess we just don't know enough. So I guess it's sometimes it's very different between something done in the lab versus an animal versus in a person. An example I think is even these new coronavirus. When this whole thing started, they said, oh, the virus can live 48 hours in plastic, or sorry, it's like 48 hours in metal and like 3 days in plastic. And where was this done? In a laboratory with seal, vacuum, everything is protected. But then in the real world, apparently it lasts for like an hour, because there's sun and there's wind and there's like dirt. And so I think, maybe it's a terrible example, but likewise, maybe in a very controlled environment, cells behave differently from what they do in a very complex environment, Like maybe once the embryonic stem cells are plastic, that's what they're good for, because they're plastic. And so maybe in the right environment, they can become something that they wouldn't become in my humanized mouse. Like if you have a mouse, you inject them because you cause damage to tissue, a little bit at least. And then if the human cells are like kind of just waiting for something to happen. And so there could be some difference there. Again, I feel like I personally don't know enough. I don't know if it's not enough, like what difference there would be. But you could imagine that, the same exact cell, but in different settings will behave differently. Like that, we can take for granted that's a fact. And now, maybe in this specific example, there's something about what you said, like the regimen, like how often you inject them, how many you inject them at one time, the person that you get inject them into, and where in the person. I think all these things are very important. So I would just need more details, I think, to look at the data. Yeah.
Definitely. Well, I will have timestamps with detailed show notes in the description below and in the top pinned comment, so everybody can check that. And I'll have STEMAID's website link there so people can look into it. From what I know about it, I've read a lot of their literature, and I've taken a master class by Dr. Denise Arinson, where she's described this science. And so what they say is basically they're doing extensive blood work on you first before they ever inject anything, to make sure that your immune system and your body is healthy enough, first of all, to receive these pluripotent stem cells. And then from there, that's where they only do about 25 million a day, because they find that they go to work, they do their job, and then the body flushes them out within 24 hours. And then they do another 25 million the next day, and they just keep doing it on a slow, small basis. And Denise Arinson had done this herself in October, and she, raved about it, and the testimonials are great. But, unfortunately, a lot of this stuff seems to be, and I could be off, but it seems to be going like very much under the radar. Whereas, you mentioned conferences earlier before, we have the internet, we have conferences. Why is it that there seems to be these companies like STEMAID that are doing what appears to be something that's like the impossible to so many stem cell experts? And that's why I go like this, because it's like, well, who do you trust? How do you know what's true or not? And so we'll go into another one here, Leo. I'm going to interview Eric Merola very soon. And he is the documentary filmmaker of a movie called The God Cells, made in 2016, which I think is fantastic. I've seen it a few times. Check the description below for the link. There's a YouTube channel with the same name, and he's done a lecture. Eric Merola did a lecture in January of 2019 that I also think was fantastic. And the God Cells is all about fetal stem cells. So they're getting these fetal stem cells from 7 to 12-week young abortions from the day of conception. And these abortions are already done. So you already brought up abortion earlier during this interview. It's a controversial subject, but it's important for people to know that the best estimates are that there's about 50 million abortions globally annually. And you're not going to stop those. I'm not going to stop them. Leo isn't going to stop them. We can try and set all the regulations in place that we want, But we've already tried that throughout many different periods of time in many governmental jurisdictions. And what happens in reality, there's a difference from reality and difference from, what you want to happen. What actually happens if somebody wants an abortion and it's illegal, then they're going to try and go to a place where it's legal, or they're going to do it in their own homes, and it's going to be way less safe. And that's not what we want. It's really bad. So the point is that there's about 50 million abortions a year. And the company in Kiev, Ukraine, that Eric Merola profiles in this documentary, The God Cells, their company name is EMCELL, EMCELL, which stands for embryonic stem cells. However, the Ukrainian language does not have the word fetal. So it's actually not embryonic stem cells that they're using from a scientific standpoint. It's actually fetal stem cells that they've been using. It's just a language barrier. So it should be called like fetal cell is what the company should be called from like a, English American standpoint. So in any event, they have been doing fetal stem cell injections, therapies, treatments since the early 1990s. And it's because when the Ukraine broke off from the USSR, the Soviet Union, now known as Russia, they got independence as a country. And Ukraine has about 60 million people. It's a very large country, a very rich culture. And so they are really the only country, Ukraine right now, that is doing fetal stem cell treatments on people, on the public. It's the only country where it's legal. Every other country, it's been outlawed. And this has to do with, again, what you talked about earlier, Leo. This has to do with politics, not science. So we need to make sure we make this distinguished here. So this documentary, The God Cells, just kind of, documents these things. And I've done immense research on it. So what do I mean by that? I mean that, there's names in this documentary of people who have gone there, a lot of Americans who have flown to Kiev, Ukraine to get these treatments in EMCELL. I've found these people on Facebook and LinkedIn. I've reached out to them kind of like as an investigative journalist, just trying to find the truth and saying, hey, is this really you? Did you really do this? Is this a scam? Are you part of a scam? And they're like, no, this is real. It helped us. There's kids that have gone there, 5-year-olds who had, things like autism, and people who have had type 2 diabetes, MS, all sorts of things that people say, anecdotally that they've had improvements on. And again, I'm going to interview Eric Merola soon. And I'd encourage folks to check out his lecture as well too. But you talk about like me, then I go into like Stem Cell 101 group on Facebook, or I go to PubMed and I do research and I talk to stem cell experts, and they tell me like, oh, there's no way, like it can't be true. And so I'm having these conflicting things, and so where is, Leo, for somebody like you, do your colleagues talk about this stuff? Like, what's going on here? How can there be this huge disconnect when we supposedly have the internet and all these forms of great communication? How do we have this like communication breakdown in this stem cell world with fetal stem cells and pluripotent stem cells? What's going on here?
Yes, it's a very good point. Again, back to the communication, science is just having to get more out there and talking to the people directly, or, to people like you, perhaps even better, have someone intelligent talking with you, or one-on-one is always enjoyable and fruitful. But so, I used to be at the Harvard Stem Cell Institute, and so every year, professors from our department would literally go to the Vatican. Like the Vatican is a stem cell research group, like interest group, believe it or not. And so stem cells is really a topic that, touches many people, like from therapy, from ethics, from just basic biology. And so I guess a couple of things to be said. One is, basic biology, we want to have models and systems as defined as possible. And so, of course, they're good to understand things, to get to the bottom of it, but they're going to miss out on some complexity. And so our body, we're still learning about it. I mean, even since I came to San Francisco, so 2016, a few new breakthroughs have been done in the human body in general, like, for example, stuff like there's lymphatic vessels in the brain. So the brain is immune, it has a blood-brain barrier, nothing can touch the brain, and yet it's got lymphatics just like our armpits and everything else in the body. And so there are immune cells, at least around the brain. And apparently these structures had not been really clearly identified and described before. And this is like, we're in the second decade of the 2000s, it's crazy. Well, like the lung is a site for blood formation. We didn't know this. And how long have we been studying the body for? Even like certain like anatomy things, So like new cell types are still being discovered. New functions for old organs are still being discovered. And so just, so in general, just to say that like, sometimes things are discovered in like non-linear ways. The linear way is I have this tissue, I grind it up, I get the cells. I sequence the cell expression levels, and then I find out that's a very linear way, like stepwise. Or sometimes you see a phenomenon, and they try to work backwards to see why did that happen. So if someone had a disease which was helped by the injection of fetal stem cells, so this fetal, this age, it's no longer embryonic stem cells to point it out, it's a fetus already. So the embryonic stem cells from the embryo, and after an embryo you have a fetus, right? It's a more later stage. These are still very immature cells. So again, for these humanized mice, we use fetal stem cells. The fetal HSC is actually in the fetus. It's not the bone marrow, it's the liver. The fetal liver is the one that makes blood. It's not the bone marrow yet. And so, just to say, like, these cells have a whole different set of biological properties that we're just trying to explore. And so what are they doing? Are they forming new tissue themselves? Are they delivering factors? I think it's a bit reminiscent of the mesenchymal stem cell discussion, right? Like, once these cells go in, are they messengers? Are they building blocks? Are they someone called conductors? They just kind of manage what's going on. We're still learning, to be very honest with you. We're still learning.
Yeah, I kind of see them as conductors, at least for the MSCs is what I'm referring to. And that's why I think the medicinal signaling cells is the most appropriate name for them, because, they signal out certain things like cytokines, trophic factors, exosomes. And yeah, really, really great answer, Leo. Maybe what I could do is, if Eric's up for it, we've been talking about this on our longevity channel, is maybe what we need to be doing to give the most service to the longevity, scientific, anti-aging, bio-rejuvenation world is for us to maybe just host a bunch of scientific minds, 20, 30 people, 100 scientists coming on to like one long Zoom or Skype call or something, and just having, oh, well, what do you think about this? Well, then going back and forth and having people's, maybe this is the form of communication using technology that's going to help solve these problems on the most efficient level, because I feel like there's a huge communication breakdown when I'm doing research and I'm hearing one thing and seeing one thing and investigating it, and then I go into the scientific community of stem cell experts and they're like, fetal stem cells, those just cause cancer, those are terrible. I'm like, well, what's really true here? Because all I really care about is what's truthful and how we can actually help the most people. Because I feel like, Leo, we have a huge misunderstanding here from the scientific community and governments and everything, where they're not taking it as a first and foremost approach that we have a huge problem, which is that we have 110,000 people dying every single day right now from aging and age-related diseases. That should be the first thing that we think about. There's a huge risk tolerance, that's off. So they don't want to take any risk because of lawsuits and legal ways, maybe the way that funding works, grant money. So maybe people like me who are outside of the scientific community and academia and stuff can actually be more supportive to the longevity, anti-aging community within academia, to maybe be like, not just me, I mean like us in general, like my longevity team and other people in this community. Maybe we can help give you guys more of a voice, because I've seen people come out of academia and then all of a sudden like, I'm free, I can now talk. I don't have to be beholden to, future grant money, worried about what am I going to say and stuff like that. So I really think there's a lot of that going on here. There's also, we cannot ignore, geopolitics and Ukraine's standpoint to America, because I'll hear like, oh, well, where's the clinical trials if these fetal stem cell stuff are legit? And MCell's done lots of clinical trials, but then it comes into like a he said, she said type thing, where you're ad hominem attacks. You're attacking people's credibility. You're saying like, oh, well, maybe they say they've been doing this, but yeah, they're just a bunch of jokers and liars there at MCell and Ukraine and stuff. So I don't think that's the case. Folks can watch the documentary and make their own conclusions. Leo, I'd love for you to watch it, and maybe we can continue this discussion, because what I'm always searching for and looking for is just ethical, moral people who want to make the world a better place. And I clearly see that you fit that profile 100%. And that's why I'm excited, to be interviewing here today. So I just talked a lot there. Any thoughts on all the, different things that I just touched upon there, Leo?
Yeah, absolutely. So I think the zoom that you mentioned, the giant zoom, I guess I'm guessing that there'll be like a Goldilocks, like a sweet spot where you have people, but not too many people, but also not too few. But
Probably
that's
too many. Maybe 5 or 6 at a time, I think, is more appropriate.
more like a panel. But just say like that's what people do at conferences already and lab meetings. You know, there's this very old video there's this magazine called The Scientist. And so back in like I think the 70s or the 60s, they had this video where they had James Watson, so discoverer of the DNA structure, and he had a lab at Harvard, actually in my old department, MCB, molecular and cell biology, as he said. And he had two students racing to find something, the repressor. The repressor is this molecule that inhibits gene expression. And so this like really cute, like half an hour, 1 hour long video, like black and white, terrible sound quality. But anyway, even back then, you know, like at some point, the narrator is like, oh, and now they're going to give a lab meeting, a group meeting. And he's like, and now they're going to use one of the most powerful tools available to the biologists, the seminar. And it really is a tool, a weapon, you know, because you're up there, you're presenting your research, and you have, you know, 10, 20, 30 super smart people that are thinking about your project with you. They're going to poke holes in your project. It's like, oh, this experiment makes no sense. Oh, this experiment is beautiful. This one has to be repeated. You know, so all these things, like you have all these, you know, brilliant minds like helping you work on your project, understand your data, see what's to do next. And so that kind of stuff already happens between scientists. Now, can we somehow have a version of that you'll have to be less technical? I'm not going to go out there to ask, hey, I got this electrophoresis. Did I use the right, you know, DNA ladder? Should I use the other? You know, these very technical questions, right? But then broader, more interesting terms, you know, can we engage more people, you know, that are also very smart, very capable, and can think about the big picture, and they're interested in all these things to work. So they'll help you, you know, work on something, they're like, I don't know how interesting that would be. Maybe focus on this instead, you know, in very broad terms. And so that kind of decisions, I think, they're more, you know, they're almost more fun to make with input of other people. You know, no man is an island, they say. And so I think bringing the general public more involved, because I feel like the way we taught science in general is such like formulaic, and like these people who are unfortunately no longer among us discover these things. And that's it, you know, that's the book. You know, they give you the book, you know, like it's done. It's not done. I mean, why do you have these piles of things in my desk? There's new textbooks being produced every week. So we're clearly not done with producing science, you know? And so I think we need that kind of discussion, that kind of engagement, even with the general public. So they know, like, okay, what does it take? How long does it take? Does the experiment take 1 week? Does it take 1 day? Or does it take 1 year? You know, different things will take different amounts of time to verify or to falsify. Maybe you think, you know, this cell does this. And in a year later, actually didn't. I was wrong. You know, you're not wrong to do the experiment. You're just wrong on what you thought the cell did. But the only way to know is to test it. Then you find out the answer. And then you should to correct yourself. Be like, you know what I said a year ago? Well, I think A does B. That's not true. Or maybe it's like, oh, A doesn't do B. And a year later, it's like, you know what? I changed my mind. I saw enough evidence that actually I was wrong. This actually does work. I just didn't believe in it at first. So it goes both ways. And I think that's what's beautiful about science and scientific inquiry in general, is that people can correct themselves in the scientific, you know, this course and the scientific record should be able to correct itself and, you know, build on itself. And that's why we have publications. And then you cite those publications and you make new ones. And so I think we need, I think just even understanding of this general principle would be already something good. Because people think it's like some scientist in the basement, you know, put two liquids together and then like something happened and that was it. Well, in fact, there's like 20 people working on this and do experiments, and like they did 20 experiments, 18 of them failed, 2 of them worked, and they showed something that we can interpret and reason with. And so that's one thing, right? To all bring the panel together. I think it will be very, very interesting and very, very important. Yeah, and then the other thing is, again, these stories, these success stories that you say, I think, yeah, we just have, I mean, the more transparent we are, the better. And so I think just, you know, judging someone based on where they're from or that's ridiculous. I really think so. And so they just have to look at the evidence. And so, of course, companies, there's some movement also for clinical trials in companies, for example, that there should be a way to somehow share the results maybe without compromising patient's identity, the intellectual property, but because otherwise you have the scenario where, a clinical trial costs billions of dollars, like 10 to the ninth dollars. And so to have 4 companies doing the same exact drug after a 5th company already found it doesn't work, that could be seen as almost criminal, right? Because many people are losing their lives and you're losing billions of dollars on a drug that is already known not to work because there's not enough transparency in the process. And so I'm not a regulation expert, right? But there's got to be a way to get better at this. That's one thing. The other thing is the compassionate use of drugs. Like if someone is going to die next week, should he or she be posed to the same standards as someone who has many years of life? Maybe not. There's arguments on both sides. On one, it's like, no, you want to save this person's life and just do anything you can. And that's, being done with like compassionate use of drugs. The other side is maybe like, well, but if it doesn't work in this person, it's not going to be a negative result. And now 100 people cannot benefit from a drug anymore because of this one person that was going to pass away. And so, it's not easy, right? So how to navigate, so 2 things again, how can we make failed experiments, failed trials kind of known to other companies and to other clinics and to the public in general? And how do we decide what are cases where we can give things that are not fully proven yet, but they're better than nothing, And I think with the COVID-19 pandemic, that's being seen a lot. All these trials are rolling out every day because they just want to save lives. We need to learn as fast as we can.
What you just said there, Leo, is the key, right? This is what I've basically been saying for 15 years, and this is what I touched upon earlier with there's not enough knowledge and awareness on this planet that right now we have a huge problem. We have 110,000 people approximately dying of aging and age-related diseases right now, every single day. And, they don't just die. There's years and decades of physical, emotional, and financial stress on not only them, but their families leading up to, their demise and their eventual death from the ravages of aging and age-related diseases. So we need to start from there. There's the problem right there. And I think we need to get more aggressive in trying things that have strong anecdotal, benefits, right? Things that I'm seeing like the fetal stem cells, the exosomes, mesenchymal stem cells, many other types of therapies as well too. If people want to try gene therapies and they want to pay for it out of their own pocket, I don't even understand why people are pushing back saying this is unethical or immoral. If you have the money and you want to try it, I don't see what the problem is. We need science to advance further, and we need it to advance further in humans in an ethical, moral way. Because we're not rats, we're not mice. I love working on rats and mice, but we're not them. That should be very clear to everybody, and we're very different. I know from just the research that I've done that things that work in mice and rats and all other sorts of animals, they just don't work in humans. People forget that we're already a very long-lived species. We want to live a lot longer, but we're already living much longer than, say, rats or mice that live about 2 years. In general. So I just want people to kind of think about that. And the problem is too, Leo, is the people who are probably going to be watching this, we're kind of preaching to the choir. A lot of them already know this and stuff. We're in this niche little tiny community. My videos don't get that many views, compared to what I believe they should be getting. Same thing with your YouTube subscribers. I'm doing the best that I can to think differently, to try and actually get more people to get interested in this type of content and realize that we can actually impact this world. And we can actually make a difference, a meaningful difference. And people always ask me, when do you think we're going to cure aging or solve the aging problem? And my answer is always, it's not the right question. It's not when are we going to do it. It's what are you doing to help make it happen? Because we are all, it's kind of like people ask that question, like they're saying, based off everything Brent, and your research, when's it going to happen? It's well, there's so many unknown variables, as you just talked about earlier when I asked you the specific question about, the stem cells, right? When is this going to be meaningful? You said maybe 10, maybe 20 years. Well, that's just one aspect of curing aging. There's so many other things too. And there's geopolitics and money and all sorts of other things involved, wrapped into those answers as well too. It's not just science. So these are things that I think are really important. And Leo, you seem like, a really great person, that I've now have in my network, and that you have me in your network too. So that we can help solve these problems, because solving the aging problem is the most important thing on the planet. And right now, I want to get it back to what you just talked about before I, started ranting here. You're talking about COVID-19, right? And we've seen incredible results from mesenchymal or mesenchymal stem cell treatments on people who have tested positive with COVID-19. And this is a huge benefit, in my opinion, for regenerative medicine and mesenchymal stem cells in particular, because now they're starting to have the light shined on them on MSCs and research. And oh man, if they can cure or help somebody with COVID-19 that quickly, what else can they do? And I'm kind of saying, hallelujah, they can do a lot of other things, right? They're basically they're modulating your immune system, strengthening your immune system so that you can fight not only COVID-19, but any virus, and really just make you healthier in general if you're getting real ones and they're done, the injections, the treatments are done properly under the proper healthcare guidelines. So this is a huge positive. So the question for you is, Leo, what can we do to create an environment within, all of science, but, the FDA more specifically, for you, you're at UCSF. What can you do? What can the audience do to create this environment where we are being more aggressive, where we are saying no? Like, we need to take a little bit more risk, on certain things that might seem more risky, because we know what happens if we do nothing. That's actually the riskiest thing. Not doing mesenchymal stem cell injections or whatever, not doing a treatment or therapy is the riskiest thing, is getting people to kind of shift their mindset too, because we know what happens. You're just going to die of aging, of age-related diseases if we do nothing. So what do you think about all that, Leo?
Yeah, well, I think the first step to solve a problem is to recognize the problem. And so I think, as you say, the fact that 100,000 people die every day from aging-related causes has surely captured people's attention. So that's one thing. The other thing is also believing that the problem can be solved, right? So maybe some people are like, okay, well, aging is awful, but we can't do anything about it. Well, I don't think that's true. And I think science has proven those types of people wrong over and over again. Like, we got to the moon, we're going to get into Mars at some point. And so science just keeps proving those naysayers wrong over and over again. And there's just so much to be gained. I mean, you mentioned the mice that live 2 years. Well, so a mouse lives 2 years, like a naked mole rat, which is not that different from a mouse, he lives 30 years, so 15 times longer. So if we understand what's the differential between the biology of a mouse and this naked mole rat, we could live 1,500 years, right? 15 times more, if you take it at face value. So how about that for a number? Like, why would people think nothing can be done if you're just looking at biology around us, all the animals that exist? There's such a wide spread of longevity. Like, we know that living things can live for a long time. Just like, like if a salamander can grow its arm again, which has, bones and flesh and skin, as I said, I think at the very beginning of this conversation, why can't we? We have, maybe they have a cell type that we don't have, whether they have a gene or set of genes that we don't have. I mean, all these things are fixable because we are in a very developed species, We can change genes. We can make cells. I mean, these are addressable, we're not trying to find the next Higgs boson, We are just what we already have, the tools we already have. Like, how can we, rearrange the kitchen sink to do all these kind of like dramatic improvements? Other thing that we know, like every species that we look at, in terms of longevity, like if you mess with the insulin receptor, it makes a big difference. So maybe there's something there too. And it works in C. elegans, which are worms. It works in the fruit fly, Drosophila. It works in mice. Now, of course, the more complex the animal, the less percent-wise you gain in lifespan. Like the worms live twice as long, whereas the mouse lives like 30%, 20% longer. But still, 20% are 20 years longer. And then also not just the lifespan, but also the health span, right? You want to be healthy during those 20 years. And so I think, once again, like, can think over time, your body stem cells, they accumulate damage. Your somatic cells certainly do. And so stem cell, either delivering stem cells or maybe in a more distant future, reactivating your endogenous stem cells. I mean, this is a logical way to go. I mean, our body is made of cells. We need to address cells. There's no other way to work with this. And so again, just these related animals, one of them lives 15 times longer than the other one. So can we understand that? Can we understand how salamander grows an arm back? I mean, all these things. That's what people, like anything, can we, engineer different cell types? Like I focus on blood cells, most accessible tissue, lots of disorders, and also the blood is everywhere, like inflammatory diseases, cancer immunotherapy. So cell therapy, so bone marrow transplant is an example of a stem cell therapy that has existed for decades with all the FDA approvals. More recently, it's been approved to use genetically modified cells, which are the CAR T cells. So a CAR stands for chimeric antigen receptor. It is artificial immune receptor that recognizes a cancer molecule, right? So you can take someone's T cells, you put this gene in, which will code for the receptor that sees the cancer antigen, and you put the cells back into the person, and many cancers that used to be incurable, they cannot be cured using this, engineered, genetically modified cells. And so that's been approved, and so we know that it's safe and efficacious to use cell therapy in general. We have the bone marrow transplant, we have the CAR T cell example. And so we just need to keep building on that. And so people just have to understand that these are not unsurmountable problems. It's just a matter of time. If we keep chipping away at it, we'll get there. Now, how fast can we chip away at it? Well, it depends how much money we have, how much time we spend on it, how many people care about it. And so I think, those numbers we can increase. Those numbers that have nothing to do with science almost, like how much money, how many people care about it. That's not science, The scientific barriers are there, that's a given, but we can, we can surpass them faster. And, maybe with more grace and elegance, the more people care about this and the more money there is into this. It's starting to, there's improvement. So, I really appreciate Aubrey de Grey because we've been talking about this stuff for decades, it used to be crazy. And I live in the Bay Area. I mean, there's people who run venture capital funds for longevity. I know them personally. So now we have the traditional, making a company that makes money model for longevity. So now it's a market worth investing in. So Aubrey was like decades ahead of his time. And so I just hope that more people jump into that train. And so, it could be stem cells. It's mostly around stem cells in the end, right? Because they're the building blocks of our tissues. It could be stem cell aging, could be stem cell metabolism, could be the aging of your immune system, could be the aging of your adipose. All this in the end boils down to just your cells.
Okay, great. So a couple of things to unpack there. First of all, with the naked mole rat, my longevity team just interviewed Dr. Vera Gorbunova a couple weeks ago. It was episode 7 on our YouTube channel. I'll put a card right above here so you guys can click on that. And she, to my understanding, has done the most work studying the naked mole rat. And it appears that it's the hyaluronic acid, which is also known as just hyaluron, which is the chemical that allows the naked mole rat to live much longer than the rat. We don't, I think, know that for sure yet, based off what Vera said, but that appears to be the chemical, hyaluronic acid or hyaluron. And so they developed this chemical from burrowing. The naked mole rat, if you haven't seen the picture, they have these teeth. I mean, they're an ugly little creature, right? And they just kind of burrow underground. And I think because they're burrowing through all the dirt and everything, they've kind of had developed evolutionarily over, thousands, millions of years, this hyaluronic acid in them. And then it's had longevity properties as well, too. So, now there could be many different therapies that we could use with hyaluron or hyaluronic acid that we could put into humans and see if it could live longer. But again, the big question that we keep running into, Leo, is how do we do this in the most safe and ethical way? But understanding that if we do nothing, then we know what happens when we do nothing. We all end up just maybe 122 years is the max that we can get if we do nothing. So there's that. And then the other thing I wanted to mention is you mentioned Dr. Aubrey de Grey. I've interviewed him a couple times, and I definitely call him a friend at this point. He's incredible. And he was so far ahead of his time, 20 years ago, getting his PhD in biogerontology from Cambridge and talking about this when his colleagues were not. And still many, biogerontologists and gerontologists are not talking about aging in the same way that Aubrey is. But he's definitely been a huge pioneer here. However, at the same time, I interviewed Dr. Natasha Vita-More, and she's been in the transhumanist movements, since the early 80s, late, I think 1979 is when she got bit by the bug. And so she, has been talking about this stuff even longer, but she hasn't been able to have the impact that Aubrey had. So the point that I'm making now is that we all have to think differently here. And I've asked Aubrey, why don't you write another book? And he says, well, because most people are watching YouTube videos now or stuff like that. So he does a lot of interviews. It's not like it's very well thought out why he does a lot of interviews on YouTube, because he believes that's the most important use of his time. And he also said that his book, which is Ending Aging, published in 2007, is still, very relevant today in 2020. It's withstood the test of time. And I agree with him. Still, a lot of people want an update from him. And so then if we jump to that logic, Dr. David Sinclair, his book Lifespan that came out in 2019, has done really well in the press. And a lot of people have read this book from all different walks of life, people who aren't necessarily interested in aging or weren't, and they've kind of been converted. And Dr. David Sinclair is also crushing the social media game, getting a lot of Twitter followers, Instagram followers, LinkedIn followers. And this stuff matters. This stuff really matters for awareness for our end goal, which is curing aging, solving the aging problem. I should actually mention right now, Dr. Aubrey de Grey. Here's another thing where we don't agree in the scientific community. He does not consider aging a disease. He considers it a medical condition. So, Leo, can we maybe talk about this and the reasons? Because there's lots of backstory behind here on funding. The FDA says that only a drug can cure, treat, or prevent a disease. So that's why, I think aging should be classified as a disease. I said this to Aubrey de Grey almost a year ago, July, in his office of 2019, and he did not agree. And so what's your stance on this? Is aging a disease? Is it a medical condition or problem, or is it neither? What is aging in your opinion?
Yeah, no, that's a good question, whether it should be categorized as a disease or not. Because from the funding perspective, if you have a biomedical research, for medicine, then you focus on disease. And so aging could fall through the cracks by not being seen as a disease. And so there's some incentive to see it as a disease. Now, as a disease or medical condition or just a big problem, I'm not sure I care too much. It's something that we want to eliminate. Now, well, what do you call it? I'm not sure it's too important, except maybe when you write a grant. And so, maybe it's okay for one grant to call it a disease, for another grant, another institution call it a medical condition. So I think these are semantics in the end. But it's important, like the NIH has a National Institute of Aging, so it does exist, but it's not as big as it should be. Because, if you think, so the NIH, the National Institute of Health, like how should the NIH prioritize money? The diseases that affect most Americans, most people in the world, maybe even, should get the most money. Well, I think aging affects more people than all the other diseases, right? And so shouldn't that be the most well-funded, institutes inside the NIH? So that's an argument to make aging a disease, because...
Leo, the thing that's so frustrating, I'm sorry to cut you off, but the NIH, National Institute of Health, and then you have the NIA, National Institute of Aging. To my understanding, most of the funding for NIA, National Institute of Aging, is going towards Alzheimer's. And it's like 95% last time I checked. I mean, this is what's so frustrating, right? This is because even if we did cure Alzheimer's, that's only going to add, a few months to people's lives or years of people's lives in general. That's not curing aging. And we know that Alzheimer's is just an age-related disease because we don't have 9-year-olds getting Alzheimer's, So I guess this is the crux of the problem why I bring it up. I agree with you that it's just a semantical and linguistical type issue. It doesn't really matter what you call aging, but it does matter in the context of funding and regulation and awareness. So this is why I bring it up. And I've created a new Twitter account called Solving the Aging Problem. And I think I want to try and build this brand. We might even create a YouTube channel just called Solving the Aging Problem, because it's a way to kind of bring people together. Say, all right, if you don't think aging is a disease, Aubrey Gray, then that's fine. If you think it's a medical condition, great. But how do I, as an entrepreneur, as a marketer, as a person who just really wants to solve this problem, how do I communicate this to a mass audience? And I think solving the aging problem is just a great way to bring all of us together with the language. What do you think about that, Leo?
Oh, no, I like it. I mean, I think we can all agree it's a problem. I can't think of anyone who would not want to solve that problem, right? I think, some topics get maybe more diverging opinions. Like, for example, should we live forever or not? Or, I think those topics will have more, distinct opinions. But I think aging, I don't think anyone would disagree that aging and all disorders that come with aging, so that's why I'm not sure aging is a disease as more as this disease cause. So many diseases happen because we get old. Like if you go to prehistorical times, there was no Alzheimer's probably, right? People never lived long enough to get that kind of stuff. Well, like, why is there an increase in incidence of autoimmune disease in more recent times? Well, because the way that we live, or our body was not built at the beginning, we did not live that long. So we have a host of problems that happen because of aging. So Alzheimer's and all these other things, these are just examples of problems that happen because of aging. So if you were to fix aging, your impact would be so much broader than just one disease. And so maybe that's why I wouldn't call it a disease, because it's much broader than that. It's a much bigger problem than any disease. It's like we study the universe, we study aging, we study what does life mean. These are big questions, I think, much bigger than, okay, how do I cure disease A, B, or C? Which, of course, affects many people, many families, but it's not intellectually not as big of a question, I would say, as, curing aging, solving aging. That's a bigger question, I think, than curing a single disease. And then I think with that, I think everybody stands to win. Sometimes people are like, well, but then it's just the way things usually go. You young and you age, and then I'm like, well, the universe is, for all we know, infinite, right? So there's
maybe there's a multiverse out there too, and there's infinite universes as well too, right?
So there's no lack of space for people. I think people sometimes are worried they're going to run out of space. Of some sort.
Yeah, it's Leo. Just the overpopulation myth, and it's funny when people first get these ideas in their head. They're pushed back. The evil dictator problem. It's like, Aubrey Gray points out. It's because just so people don't know, to be very clear here, people say, all right, well, if we solve aging, then what happens if dictators are dictators, for thousands, millions of years? Aubrey Gray points out that a dictator job application isn't exactly something that people are lining up for. It's a very risky job. And I'm just an optimist, and I also don't think that these are valid reasons to not solve the aging problem. Again, because it always goes back to something that I repeat all the time. Aging is killing 110,000 people every single day, or aging related diseases on average. So it's already a huge problem. It's killing way more people than Kim Jong-il or African dictators could ever imagine killing, even if they tried their hardest. They destroy their whole They couldn't create enough humans to kill them enough as aging is already doing. So the point is that it's a problem that needs to be solved now. And all the other stuff, the overpopulation stuff, we don't have to get into that, Leo, right now. We know from running through these scenarios with people and thinking about it that they're just ridiculous. You could fit the entire, 7.8 billion people in a small part of Texas right now. The question is the carrying capacity of the Earth is important, and that is based off science and technology. That is based off, do we actually build the technologies that are necessary for people to live a high standard of life? How do you live long? Well, one of the ways to live long is have a refrigerator and a freezer. These things weren't invented a couple hundred years ago. That helps you live longer, right? Because or you're going to be working your ass off, going to the grocery store every day or gardening in your backyard or whatever. So the point is there's technologies that improve our life as well too. It's not just as simple as saying, oh, if there's more people, then we're going to destroy the planet. It doesn't work like that. It's more complex than that. Is that right, Leo?
Well, and then there are more planets, So I think what I was trying to get at is that because the universe is infinite for all we know. It's not like we have to worry about real estate right now. I think we'd rather worry about, maybe care about ourselves first, and well, ourselves and others around us, obviously, and also animals and plants, obviously. I think very important, like biodiversity in general. But so I guess what I want to the point today is that, like, imagine because we solve aging, now population from 7 becomes 15 billion. I mean, think about that. If you had, I don't know how many people now are working on getting us to Mars. Not too many. What if you multiply the number by 10, by 100? Because you just have more people. So if you have more people, you'll have more, the total number of, doctors and lawyers and bakers and people working on getting us to Mars will also increase. And so, I just feel like it's a problem that has a solution in itself. Because by making more people, you're also making more thinkers and workers to solve the problems that having more people creates.
Yes.
This is my optimistic view of it. So that's why I don't see it as a real problem, the overpopulation, because, well, there's more planets out there. And of course, it'll take decades, but it's not going to happen tomorrow either, So I feel like the timing, I would hope, would align nicely. Maybe we can live in different planets. I mean, think about like Star Wars or Star Trek or like these are all feasible scenarios. Once we unlock the capacity to be in different planets and have, fast transportation between them. I'm used to learning physics. You can have like nuclear fusion as a way to power things. You have renewable energies. All these ways to power. In the end, again, we should, we should be the best, take care of ourselves and the planets that we inhabit. With its animals and plants. Maybe other intelligent species that we're gonna hang out with. The future is bright, and I think maybe that's part of the reason why I got interested in all this. Like, there's just so much to see, so much to do, so much to look forward to. Like, why do you have to stick around for only 100 years? Why not like 1,000 or 10,000? Yeah. There's so much to do.
The deafness, people who don't want to live as long as science and technology will allow them to do. A lot of them ask me, like, don't you think you'll get bored if you end up living thousands or millions of years? And yeah, I laugh too. I'm like, I don't get bored right now. What makes you think I'm going to get bored later? Like, science and technology is making reality more interesting. I go to sleep every night with like a whole Rolodex of things that I still didn't get done that I had to do. So boredom isn't even a lexicon. Maybe if I was imprisoned in solitude confinement or something like that, solitary confinement, maybe I would get bored at that point because I would meditate so much that I'd run out of things to meditate about. But as long as I'm like free and we have the planet that we have now and the internet and people, no, I will never get bored. I can be very confident saying that, even millions or billions of years. And then also, if you ever do want to end your life, nobody's ever stopping you from committing suicide. You always have that option if you want to end your life. I don't support it. I don't agree with it. I will encourage you not to. But if you want to do that, you can always do that. So we can go on and on with philosophical things. Let's get back to the science, Leo. With you being your cellular, molecular, biology expertise, I'd love to know your opinion on exosomes, because exosomes are really exciting, and I have studied them quite a bit. Just so I've interviewed the CEO and founder of Kimera Labs, which is an exosomes manufacturer. They're down in Florida. His name is Dr. Duncan Ross, and I have also followed Dr. Ed Park, who's a medical doctor who went to Harvard as an undergraduate. He's a couple decades older than you, but he got his medical doctorate from Columbia University and also has a master's in public health from there as well, too. And he runs an anti-aging practice down in Orange County called Recharge Biomedical. And he has been injecting not only himself, but also his mother multiple times, but 38 other patients with the Kimera Labs exosomes over the last 14 months or so, since March of 2019. And I've read each and every one of these blogs as he describes, the patient's condition and talks about what their pains are, the treatment that he gave them, and then the follow-up, their results. And he even, a few blogs ago, maybe it was blog 34 or so, did a whole synopsis of the 1 year anniversary of him injecting all these patients with exosomes, and he went through each and every one of them, and he didn't name them by names, but he talked about their condition, positive, negative side effects, what's happened. So very extensive. And for even some of these people who he's treated, they've done YouTube videos to kind of anecdotally explain, what their condition was, how they're feeling now, if they're happy or not. And let me just summarize and say, it is absolutely incredible what is happening to these people, the benefits that they are getting from the exosomes. Overwhelmingly, there are some people who have not had results. That's a very small percentage. And there are a few people who had some negative short-term side effects, but nothing too bad. So these exosomes from Kimera Labs, they've been isolated from a placenta of a healthy human birth. And so that's where they're getting these exosomes from Kimera Labs. And so with that being just laying the groundwork there, what do you, Leo, know about exosomes? Do you study them at all? Are your colleagues excited about them? What's the deal with exosomes, in your opinion?
Yeah, no, these are very interesting. I think the first time I ever got exposed to them was actually in the cancer field. They did like cancer cells release exosomes, which are these like, small particles with a membrane around them that carry mRNA, they carry proteins, they carry information basically inside them. And so there's some work, very elegant work, showing that you have a primary cancer and then it can metastasize, right? It can, go to different sites. And so there's some work suggesting that the cancer cells release exosomes, which kind of like precede, different sites of metastasis. And so again, the idea like cells have this way of communicating, of having their voice heard, if you will, via exosomes. And so it's a very fascinating structure. It's actually back in my PhD, there's a classmate of mine that was working in George Church's lab, and he really focused on exosomes. So he was trying to, sequence the RNA found inside exosomes. So again, trying to decode the message inside a bottle, if you will. Like the cells are in the ocean and these bottles with message inside them, and trying to really read that message. That's what he was focusing on. Ever since, it's been almost, almost 10 years now, and a lot has been learned for his exosomes. And again, the fact that they can have not just RNA, but also proteins inside them and other molecules. And so I see some potential there. You could imagine a scenario where, we mentioned before that, the mesenchymal stem cells or the medicinal signal cells, sometimes their job is to deliver a signal. So can we do away with the mesenchymal stem cells and just use the exosome that has the signal? Pros and cons. I mean, the exosomes are smaller, easier to make, but at the same time, they don't have the same, location, zip code properties that the cell does, right? Or at least not clear yet. So there are pros and cons. We could imagine for some therapies, like the exosome is the way to go. Like you don't need the whole cell. You just need the exosome to have the signal, the molecule that you need, and to deliver that. Yeah, and I think there's some targeting potential because, again, exosomes have been found to have proteins on their surface. So you could try to engineer an exosome to have, something on its surface that will guide it to a specific place. And so, I think exosomes are really up there, and I think they could become more exciting options as, say, nanoparticles. So nanoparticles that I think ebbs and flows, and we used to talk a lot about it, the nanoparticles, and then they kind of went out of fashion, if you will, and now I think they're trying to go back up again. But so nanoparticles, the idea like can use, these small particles that will be coated with stuff where they'll deliver something, and I think exosomes are like the, cell biology response to that, that now we can have fragments of cells that can deliver cell messages. And so I know that, and so working patients, I think it'll be interesting to keep following up, right? Because again, as usual, what happens in the petri dish is not always the same happens in the mouse and in human. And so again, our body is so big compared to a tiny plastic dish. Like, do the exosomes go where they should be? Do they get lost along the way? How many exosomes do you need to inject? The dosage. So I think this will be very interesting to follow. And so I think exosome could be used for many things, because depending on what you load inside those exosomes, you can target many different disorders, right? So I think you mentioned this company, they're treating patients with different conditions, right? So they're likely to load up their exosomes with different molecules inside them to help these different types of patients. So I think it's very interesting work.
Definitely. And, like any competitive landscape in the business world, there is, some mud raking and all this kind of stuff. So there's a company, Direct Biologics, which also manufactures and distributes exosomes. And, I have male pattern baldness. I've been balding, for over a decade. My dad's bald. My dad's dad was bald. So I feel like I've actually kind of made it further along in life than they did at their age with the hair, probably due to my healthy living, but it's genetics to a certain extent. So I've looked into reversing male pattern baldness. I did have the stem cells in December 2018 in Mexico. I did have about 10 million of them microneedled, derma rolled, into my head. And I don't think it really did anything, and I wasn't expecting it to. Josh Kettner, the owner, founder of Dream Body Clinic, where I had the stem cells injected, he told me that I was too bald, and I watched his videos and read the literature and kind of realized that I was probably too bald for it to have any improvement. It has shown help for people who are just kind of starting to bald a little bit. So that didn't help, but I've researched on YouTube and I actually know one of my subscribers, Bob. He had a hair transplant, and now some of these companies in Austin, and his was in Atlanta, they are doing exosomes injections from Direct Biologics for male pattern baldness. And he sent me pictures, and it looks like his hair's growing back, and he thinks that it is. And some of these hair transplant doctors have actually injected themselves with exosomes. And I've watched some of these YouTube videos, and their hair has grown back, it appears, from the exosomes. So something's going on here, and it's frustrating to me that this is just tiny little niche world at the very beginning of this, where I just want this to happen faster and I want more people to know about it, but yet everybody is just worried about a bunch of nonsense, essentially in the world, things that don't really matter, whatever the mainstream media is telling them. Meanwhile, you have this exciting world of regenerative medicine just, coming to life right now. And I know it's equally probably frustrating for you as well too. But Leo's doing something about it. So guys, again, support Leo, subscribe to his YouTube channel, follow him on social media, on LinkedIn, Facebook, Twitter, Instagram, links in the description below. I mean, we have to make people like you rock stars. This is my goal. You should have millions of followers on all these social media things. If we are living in that world, then we're going to solve the aging problem. So the question isn't when are we going to do it? It's what are you going to do to help make that happen? That's what I truly believe. So were you aware of any of this stuff about exosomes, Direct Biologics, Kimera Labs, people injecting these now? Are you aware of this world, or are your colleagues aware of this stuff? What do you guys think about this?
Well, I think it's more recent than the stem cell clinics in general. And so I think, yeah, I've heard of direct biologicals for sure. And so again, even at UCSF, there's people working on exosomes, in mouse models mostly still. But again, they just implicate in such a wide range of contexts. So in cancer, as I mentioned at the very beginning, and all sorts of things. And so I guess a couple of comments. One was, you mentioned making scientists rock stars, and actually I should say I had a very fun experience at the Cold Spring Harbor Laboratories there in New York. Jim Watson used to be the director of them. And so this place is like, it's all labs, and they have conferences there like every week. Every week's a different conference. They're constantly hosting conferences in this place it's close to New York City. And so there is this world where scientists are rock stars. There's this really cool thing where you go and there's a gazebo, there's like a bacteriophage on top. So the virus that infects bacteria, there's very geometric shape and then little legs. And so that's the top of the gazebo. You go to another building, there's like a statue of DNA, being transcribed into RNA. And then you go, there's rooms that have kind of portraits or, like those like a basketball Hall of Fame, but for scientists. And so it was kind of interesting to me to be immersed in that world for a week where scientists are the rock stars. They're the ones making discoveries, they're the ones that are famous, people want their autographs. They even make I think you have it somewhere, they make a caricature. If you go up to there's this guy there, very talented. And so I thought it was really fascinating, place to just be immersed in. And so I think there's so many cats on the internet. You could make some more space for some useful science as well. So that was one story, and then the other one, so back to the exosomes. So yeah, so people working at UCSF, at I think all major universities and beyond, and so I think in people it's more recent. So I'm not fully aware of everything, but specifically for the male pattern baldness, there's also hair stem cells. So if you look at hair, also the hair follicle, there is a hair follicle stem cell, and so you can follow excellent work by Elaine Fuchs, who is a very famous professor at Rockefeller in New York, and other people. And actually recently, articles just came out that they were able to grow skin from stem cells, this skin and hair. So that's been a challenge, right? Like you can remake skin, like if a burn victim, right? You can make skin. I should say, actually, back in 2018, there's this really crazy publication where this kid had this disease of the skin, that the skin literally, like, it boils, it's all inflamed, it's all coming off. It's a terrible disease. And this kid was cured by using a stem cell transplant, a skin stem cell. Like, this kid was in Italy, and they took biopsies of, like, whatever skin he had the best skin or parts of him. They isolated the skin stem cells. They grew skin from those cells in a laboratory, and then they transplanted back into him. And then these skin stem cells, I should add, they were genetically modified to correct the mutation that was causing the disease. So I think in general, important to emphasize that regenerative medicine, it's almost a new way to do medicine. Because so much medicine is like you're trying to alleviate symptoms. You're trying to make it less bad. And regenerative medicine is actually going at the root cause of the problem. Like if this this gene is causing problems, then correct the gene. Don't give a drug that is gonna reduce the levels of this compound made by the cell next to the cell that has the gene defective. You actually want to correct the gene, or if it's a cell missing, then put more of those cells in. Or there's some inflammatory process ongoing. Well, then stop the inflammation with cells or with something that comes from these cells. And so I think in general, that's the idea of regenerative medicine, at least in my mind, is to get at the root cause of disease. And so again, in this case for the skin, they took the skin stem cell, correct a gene in those skin stem cells, and grow in the laboratory patches of skin. And this is perfect skin with the right gene. And then transplant back into the kid, and now the kid is cured. Again, this is not rocket science. This if it was done now in this small-scale study, to publish a paper about it, we can do 10 people, 100 people, 1,000 people, how many people as there are that have this disease. And so there's something holding back that has to be get rid of. People have to understand that this is extremely important work and it's being done already. Like, we're not even reinventing the wheel. This has been done already. Now we just have to scale it up to make it better, to make it safer, to make it apply to more people. So universal stem cells is one example of something that can make it accessible to more people, right? If you don't have time or money to make your own iPS cells, then you can have a centralized bank, to have stem cells already made for you. You don't have to worry about that. And so I think that kind of stuff is what should really get people off their seat and excited about this, is that this is already happening. We just need to make it available to more people. So it will make it even cheaper, even faster, like CAR T-cell therapy for cancer. It's not stem cells, it's an immune therapy, but it's very expensive. It's like $500,000 per therapy. But now imagine you have 10 times more centers doing it. Now maybe you can make it down to, $100,000. So, you slowly, it's like genome sequencing. Genome sequencing, the human genome was like $1 billion. And now I can go to Nebula Genomics and get my genome for $500. And some people even claim you can do it for like 100, So over time, these things get cheaper because it's just the way technology goes. Like, we want to make biology and medicine be almost as much as technology as possible, because no one doubts that computers get faster every year and components get cheaper every year. And so no one doubts that, right? That's very visible to the naked eye. So why can't biology be exponential like that if we have the technology? So it's really just a matter of having more people working on it and more money put into it, and sometimes, frankly, more interest. Because people think it's science fiction, but it's not. All I'm telling you today, I didn't want to watch any movie about this. This is all from nature and science, and I have a very boring desk here. I don't read science fiction. I only read science reality.
Me too.
So this is all. They say that reality is stranger than fiction. I think some physicists said that. And I think he was right, because science fiction sometimes is behind actual science. Because the stuff that we do and see every day, it's crazy stuff what we can do.
Leo, on that note, do you find that when you start talking about, the ideas of reversing human aging and living indefinitely, things like that, I don't like to say live forever because, you can never say that I've done it, I've lived forever,
Yeah.
because another second always ticks by. It's not a scientific statement, right? You can never prove that you've lived forever. And even if you do live indefinitely, the universe or multiverse or reality will probably end someday, and then you still hadn't done it, you hadn't lived forever. So it's just a weird word. It's going back to like semantic problem. So I just like to say living indefinitely, or living as long as science and will allow you to. So but my question is, do you notice that when you do talk about with just friends, family, random stranger on the street, about reversing human aging, their pushback seems to almost always be, to me, not about science, not about logic, not about reality. It's just an emotional pushback of like what they've been taught from when they were young, of that like it's not possible, it will never happen. People have been searching for this since the beginning of human history. And generally people are pretty negative about it, in my opinion. Do you share that opinion from your experience?
Yeah, it's a bit strange. So again, like I feel like I almost live in a bubble because I live in San Francisco, so maybe I have less of the interactions than in other places. But it is still true. Like for me, it's a bit strange that people are very quick at believing that something cure cancer, but if something will cure aging, they're like, no, that's not possible. I think you put it perfectly right that there's some intrinsic negative feeling, or like no suspicion about work on aging compared with work on like very complex problems. Like why would it be at this time they cure cancer but not the previous 99 times? So people always believe that in general, let's say. But if anything with aging or living longer, that doesn't seem somehow as like, oh, that's not possible. So I don't know where that comes from. That's an interesting question. Like why, where did it start? That like cultural almost conditioning that some problems are just outside the scope of what science can do. I really don't know where that
Yeah,
came from.
I don't really know either. I've thought a lot about it. I have theories and I have some pretty strong beliefs on it, but I don't know for sure. And I think everybody has a little different background, but it's definitely a thing, and it's weird and it's frustrating. And people are just ignorant about so many things about, biology and aging and cancer. Like, for example, the best estimates that I found is that if we actually do cure all cancer on the planet for humans, that will give humans about 2, maybe 3 years of more life at best. Then it's kind of like on to the next problem. So that's why aging, Vitalik Buterin, the founder of Ethereum, billionaire wonder kid, he is very interested in reversing human aging, and I'm going to try and work to network to introduce myself to him and interview him. And one thing that he tweeted recently is that aging is like the final boss. So if you're not a video gamer, what that means is you even probably remember Super Mario Brothers. You got like 8 levels. At the end of each level, you have a boss. Aging is the final boss, and that's as the first time I had heard that, in Vitalik's tweet, and I think that's great. We need to all hive mind this together and figure out the best ways to communicate and change people's minds, because changing people's minds could then get more awareness and more funding for people like you to then, as you already talked about, Leo, actually go into the lab and have the funding to actually do the work that needs to be done to figure this stuff out. So yeah, I'm gonna try and get in touch with Vitalik, and I'm connected with his dad on LinkedIn, so that could be a good route. And I'd love to interview his dad anyways, because I see that Vitalik's dad basically created Vitalik in more ways than one, because Vitalik's dad has been interested in, cryptography and libertarianism, cyberpunk type guy, and interested in reversing aging for many years. So it's not a coincidence that Vitalik has been interested in these things from a very young age. As I believe we sit here in 2020, I think he's only like 24 years old or something. He created Ethereum like 7 years ago or something like that, 6 years ago. So the point there is that let's get your kids interested in this stuff. I have a 7-month young child right now, and let's change the language. I don't call him 7-month old. He's 7 months young. A lot of this stuff could just be in our heads. We could be creating the nocebo effect in our own biology with the language that we use. Language is really powerful. So I have a 7-month young son, and I'm not taking the advice of most people. I'm going to teach my son all truth, science, reality. He's not going to think that Santa Claus is real. He's going to learn about reality as quickly as I feel like he can. And I think that this is controversial to some people, but shows you how I think we're still in the very beginning of like the scientific mindset integrating and becoming part of our massive culture. What do you think about that as a higher level idea there, Theo?
Yeah, I think we need a second enlightenment, pretty much. Like in the first phase where people were dying from Black Plague and we didn't know anything. We've come a long way from that, so that's good. But now I feel like we need a second wave of that, where I think there's so many beliefs that are not founded by any science or logic, they might have to go away, for our own good. And so also, it's almost a duality of like sometimes people make, even scientists sometimes, they'll make, in the laboratory versus outside laboratory, they'll make decisions differently based on it's like, oh, really? I mean, why would the laws stop applying, once you leave the walls of the lab or once you talk with someone who's not, So I think, yeah, there's a lot of work to be done there. I mean, people are more than just science, obviously, but at the same time, I think that we build the world using science. I mean, of course, there's many non-scientific endeavors, but I think even those are helped by science. Like you cannot travel the world if there's no airplanes to get you there. And so
it'd be a lot harder to get there on boat. Be a lot longer travel.
Right.
Leo, I believe that it was Carl Sagan who said, I'm paraphrasing, but maybe I'll get this right. He said, we live in a world based primarily on science and technology where hardly anybody knows anything about science and technology. In other words, they're specialists, and you're a specialist in cell and molecular biology, and you're focusing on stem cells, but there's not that many of you, and we need more. So on that note, Leo, can we get into the details of your day-to-day work, your research, your interests at UCSF? What do you do on an average day, and who do you work with? Like, what's your team? Are you leading the team? What's going on? All those details would be great.
Yeah. So we usually in academia is you go to college. So you're in college, and then you do your PhD, and then you do your postdoctoral fellowship, and then hopefully you run your own lab as a faculty, right, as a professor. And so right now I'm in the postdoc part of that journey, right? So I finished my PhD in 2016, as I think you've mentioned. And then after that, it's been now 4 years that I'm here at UCSF for my postdoc fellowship. And so what that means is that I work with 2 professors, QZ Tang and Jeff Bluestone. I'm here at the Department of Surgery at the Diabetes Center at UCSF. And what I've been focusing on really is the regulatory T cell. So as I already alluded to, so my day-to-day, or let's say week-to-week maybe, because sometimes it takes more than a day to do things, is, I get people's blood. So peripheral blood, you get like 500 ml bag of blood, and you can then purify cells from it. So there's all these things that we do. You do a Ficol gradient to separate the plasma from the cells, from the red blood cells in the bottom, and then from those you use fluorescently labeled antibodies to stain those cells. Use this fluorescently activated sorting machine, which you can then basically purify the cells that we want. And so in my case, from all this, I care most and foremost about the regulatory T cell. So it's a group of T cells, also the adaptive immune system, and they control immune responses. So for example, let's say you have a viral infection. If the virus is inside your cells, and so your T cells catch up on it, and they kill your cells in whatever tissue it is, and then at some point, it's over. All the viral infected cells have been killed. So now the immune response that was like at the peak has to come back down. Because if you were to continue on and on indefinitely, you just cause tissue damage. It will be bad for you. And so the Treg really is in charge of controlling that. It's conducting the immune response to make sure like it doesn't go overboard. And so there's many disorders where this does not happen properly. For example, in autoimmune disease, you have T cells in your body that attack your own tissue. So there's no infection, there's nothing. There's just, they just attack your pancreatic beta cells in type 1 diabetes, or your nerve cells in multiple sclerosis. And so these are terrible disorders. It's very unclear how they start. We know there's a genetic component, but it's a very small part of the story. If you do even studies between twins, sometimes if one twin has multiple sclerosis, the other one only has it like half of the times, 30% of the time. So there's like a big, if you will, like black matter of autoimmunity that we don't know where it is. It's the environment. It's all we can say. Could be, bad luck, a viral infection that triggered it, something that you eat, something you got exposed to. And so these cells, these Tregs, regulatory T cells, are involved in that. In the sense that if you were to now put these cells in, you could stop this unwanted inflammatory immune response from happening. And so that's been most of my focus. So to get these cells, to genetically modify them, to target them to different tissues. So my day-to-day will be, I get the blood, purify the cells, I can genetically modify them with CRISPR, Cas9, right, or with lentiviruses that code for different genes that I want to put in, if it's a synthetic gene. Or you can use CRISPR for two things. You can either destroy genes, or you can put new genes in using a molecular combination. So I work with that kind of stuff. So you change the genome of these cells, and then you grow them in these petri dishes, like, they keep multiplying. So I can fill a whole incubator, which just is like this 37 Celsius, space that the cells think they're inside your body. You just trick them into thinking they're inside someone's body. And then you use them for experiments. And so some I do are in vitro, meaning that they're just in a petri dish. You mix different cell types together. It can be in animals, so you can inject mice with these cells. And so the mice, they're valuable because then you can study how the cells behave inside someone's body. It's not a perfect model, but no, they can go. I find them in the bone marrow. I found them in the spleen. I find them in the lung. So they go to different organs in this mouse. And so, of course, the goal is to put them into people. And so UCSF, actually, and other institutes around the world, I think there's over 50 trials using regulatory T cells specifically, where you put T cells to people. And so where we are right now is that these cells are safe to use, so the people don't get any worse from getting these cells, but we don't know the efficacy yet. So now the phase 2 clinical trials to make sure that they actually bring any benefit. There's some evidence, like in the organ transplant field, where once again, we have an unwanted immune response, but this time it's not against your organ, it's against someone else's organ, but that you want it to be yours because it's helping you. And so a big problem now is that, either people die because they can't get an organ. I think it's like 10,000 a year. So, much less than aging, but still a number. And so you can imagine different ways. One is to give them very heavy immunosuppressive drugs like, steroids and other tacrolimus, that really your whole immune system shuts down. And so that means that if you get like a little cold, you're going to be in trouble. But the alternative is to die because your liver doesn't work. And so that's kind of the line, the tightrope that these patients have to walk. Or ideally, you have a more targeted strategy. So that's where these genetically modified regulatory T cells come into play. So we're trying to generate cells as living drugs for inflammatory disorders. So it could be to prevent an organ from being rejected, could be from stopping an autoimmune disease from keep going. And so that's my day-to-day. So eat people's blood and then work a lot with lab animals, and then also, prepping for the human trials as well, which again, there have been almost 50 of them, and it keeps going. So there's some studies showing that with these regulatory T cells, indeed, you get less bacterial and viral infections in transplant patients, which again is a problem if you have just these heavy drugs. The immune system is just like destroyed. It's like the bubble boy, basically. Like they're alive, but they have to be afraid of everything. And so, replacing these drugs with cells is already giving big benefit because now they get much fewer bacterial and viral infections. And so that's really the kind of the short-term, medium-term goal, is to really use these cells for as many disorders as possible that could really benefit from having this specificity. Because right now we got very good at immune suppression, so shutting down the whole thing, and that's good for acute organ rejection, that's good for, other things. But now we need to move on from immune suppression to immune tolerance. And the only way to achieve that is using cells, is using regenerative medicine, right? So I did, again, you're going to use cells to fix problems with your body, to get at the root cause. If the root cause is the immune response being dysregulated, then you got to put in the regulators, the regulatory T cells. So that's my short and medium term focus. And of course, once we have this, I think we can really help democratize regenerative medicine. So now, I think it'll be almost a race. Like, who gets there first? The people that engineer stem cells to make organs, or people that engineer the immune cells to not attack the organs? I think it will be an interesting, race to follow. And, I've worked on both sides, so I like to think I'm as impartial as possible, because I think both have merit and both have a place, good things, bad things. So if you engineer the graft, the organ, it might be a bit easier because you can have the stem cells in the lab and then you make the organ. But, making organs is hard. So it's easier to manipulate, as of today, 2020, right? It's easier to manipulate blood cells than to manipulate like a heart or a liver, like the whole thing, or even the stem cells that make that whole thing. And so we have a bit of an advantage with the immune system engineering, but at the same time, the immune system is very complex, like it's multi-pronged. Like if you touch one thing here, something else makes up for it. And so I feel like I'm constantly racing against the immune system because I change one thing and then something else changes. And then I go, cover that hole, and then something else opens up here. And so, both approaches have pros and cons. And so that's how I spend most of my days, is doing these things or thinking about doing these things.
A cat and mouse game to a certain extent, right?
A little bit. Because, again, the immune system, that's what it evolved to do, was to circumvent any perturbation to the system. Like homeostasis, I guess, is what we're trying to get at. We want to reestablish homeostasis in a system that is so deranged that it's found a new local minimum, if you will, right? Like an autoimmune disease, that's the new normal. The new normal is these cells being killed every day. And so we want to bring that new normal, push it up the hill, and then bring the healthy normal. And so along, going, it's like an uphill battle, really. So like along that battle, the system itself is going to try to keep, pulling you down. And so we hope that these cells, with their inherent complexity and programmability, you can program them more so than a small molecule. That's the hope, is that this way we can really make a dramatic change in these people's lives. And again, the next step is to apply that more broadly to the regenerative medicine as a movement, if you will. So now, if your body is a car and needs a new piece, we should make it as easy as possible to get that new piece. It could be from engineering the stem cells, could be from engineering the immune system of the recipient, could be doing both. But so this is the idea. That's why I said 10, 20, 30 years, that's what I'm going to keep working on, is to make this a reality for as many people as possible.
All right. That's incredible. And awesome explanation, awesome work that you're doing. Would you yourself ever, consider getting stem cells right now? And if so, like, how would you go about that? Like, for example, for me, I just had a really bad ankle sprain when I was 20 years old, 3rd degree. For those who don't know much about ankle sprains, there's 1st, 2nd, 3rd, and 4th degree. 4th degree is when the ligaments and tendons completely tear. 3rd degree is like close. And I had lots of 1st and 2nd degree ankle sprains throughout my childhood playing basketball. I got the ankle sprain when I was 20 from landing on a guy's foot coming down from a rebound playing basketball. It was so painful. It was black and blue all the way up my shins, down to my feet. I'd never seen this, never heard of it. I didn't even know this was possible until it happened to me. I was on crutches for a month. And I was a stupid 20-year-old kid. I didn't do the proper, rehab, and it never fully healed. I just had bone spurs. And so all through my 20s and early 30s, I was just kind of like, oh man, this never like fully healed. And I never, looked into it. So with all my stem cell knowledge, I just started doing even more research around 2017, 2018. And I personally, found the clinic that I thought was right for me from a financial standpoint and technology standpoint and all that. And I strongly believe that it's dramatically helped me, not just, so I had it in my ankle, my knee, and then my shoulder, because I grew up playing baseball and now I play adult dodgeball. So I've been playing dodgeball the last decade. So I had it, 32 million mesenchymal stem cells plus my PRP platelet-rich plasma, which they, extracted my blood, spun it up in a centrifuge, added that in, and then they put in 0.1 milliliters of calcium glutamate. 32 million in my shoulder, 32 million in my ankle, 32 million in my right knee, 22 million in my right ankle, and then 200 million IV into my arm, plus some vitamins. So that's what I did, and I strongly believe that it's helped me. But I understand if people, question it or say, "Oh, it's just anecdotal." I didn't get an MRI before or after because I just really wanted to save money. It wasn't included in the price; it would have cost me more. I knew that I was injured, so that's kind of my story. But Leo, if you had a chronic musculoskeletal condition like that or something, would you ever consider doing something that I did, or would you go in America? Like, do you know much about this as a stem cell researcher? Do you know about this crazy world of like medical tourism and stuff? Because it's like, personally, like, I just had to do a lot of research on this, and there are a lot of outlets now to do this with like Stem Cell 101 Facebook group and things where people are just kind of like me telling their story. It's a different world now in 2020 than it was 20 years ago. So I mean, do you know much about this? And if you can, I'm sure you've at least thought about this, like if you would ever do something like this yourself if you needed to. What do you think?
Right. No, I mean, I think, it's a very discussed topic. The stem cell treatments around the world and how it's also a growing market. Like a company that was co-founded by one of my PhD advisors who's just raised $0.7 billion, so 700 million. So, these are all big numbers because, again, working with cells is so expensive that you can quickly go through tens of millions of dollars. That's why, again, it's also important to people understand that it's not like shooting a movie, This is, fancier stuff that needs a lot of, well, I guess the thing is that people accept that a movie has such a high budget. Why can't science touching science fiction research not have a big budget as well? And so, that's just an aside. But so I think, if I had such injury, I'd definitely consider it. And so I should say, I have said two examples where stem cells are being used. There's a bone marrow transplant, everyone accepts, right, that it is being used. And in Japan, there's also trials. And there's actually another example, which is actually oral surgery. So in oral surgery, it was brought to my attention by friends. I'm not in the industry myself, in dental business. But so in oral surgery, they use, the platelet-rich plasma, and they use freeze-dried bone from someone else to reconstruct your jaw or like whatever you need done. So that's an example where, you must have stem cells that are helping, rebuild this lost tissue. In this case, it's bone tissue, and then the platelet-rich, so plasma. So these are things that have been used also for a long time. And so again, I think if I were to do it myself, I definitely know people I would ask and then really look into it. And I can actually read publications or look at the data. So I have some sort of like unfair advantage, if you will. Because I know exactly what markers to look for.
Cheat codes. You got a lot of cheat codes, right?
Yeah, a lot of cheat codes. And I know the instruction manuals from, front to back and back to front. And so I will definitely consider it. And again, I think it's just interesting to me, sometimes almost cultural, like some examples of stem cell therapies, and in tissue-based, the regenerative medicine, basically regenerative medicine, it's been there, but now can we take it to the next level? And so I don't know why there's so much resistance to taking it to the next level. I mean, I understand it has to be safe, it has to be effective, but without doing it, we'll never know, number one. And then, what really gets in the way of knowing if it's working or not is not having good regulation, such that people have to go abroad or they have to go to some I think you do a service to everyone if we work towards making it more transparent, not just harder, because then we don't have the data. We'll never have the data. If it's not regulated, we'll never have the data. So the proliferation of unregulated, and then there'll be some horror stories that could be completely avoided if there was more of the good, regulated, safe, and effective stuff. We should know based on preclinical trials using animals like mice or even monkeys. Like we do this for vaccines, for example. We can do the same exact thing for stem cell therapies. And in Japan, again, they are. They treated some neurodegenerative disease in monkeys with stem cells in Japan. They have the data, and they're pushing along. And so why can't we in the United States do the same? Or in Europe, other countries? I mean, this is all feasible. Again, it's not rocket science. We're not finding a new Higgs boson. We're just things we already have. We already know cells, already know DNA, already have needles to inject things, already have animal models in place. I mean, we are at all of the tools. It's like we're just cooking something. We're not inventing fire. So it pains me a little bit that development has been slower than it had to be.
but I'm just trying to do the best that I can with the resources that I have to push this movement forward. And that's why I, had my wife join me down in Nueva Vallarta, Mexico, and recorded on video all of my injections to be as transparent as possible. And then I did follow-up videos to talk about not only how I was doing, but what lifestyle I was living as well too, because I think this is really important, because I was doing like lots of really healthy things, getting, first of all, great sleep. I think sleep is super important. I should never interview anybody about health without talking about sleep. Like, get your 8-9 hours of sleep every single night. It's really, really important. It's the foundation of health, in my opinion, from according to Dr. Matthew Walker at UC Berkeley, sleep scientist. He's a sleep scientist for Google. I highly recommend his book, Why We Sleep. I've done a book review on it, which I'll add into a card right there. I've interviewed the sleep doctor, Dr. Michael Brews. He's been on Oprah. He's been on Dr. Oz over 40 times. He's been on lots of mainstream media. Kelly and Ryan Seacrest. Sleep is just so important. So I was doing all these things. I was doing chiropractic work. I was exercising. Intermittent fasting helps your body produce more and better stem cells. Is that, Leo, is that accurate from your research as well, that intermittent fasting helps your body produce more and better stem cells?
Well, so what I know is that if you go to any longevity meeting and they ask you, okay, what can I do right now for longevity? What they tell you is eat less, do fasting. That's the one thing. And actually, it's backed up by pretty old studies. So even though it sounds like a new trend, at least in the scientific world, it's not new at all. I mean, there's old studies showing that if you give the same exact total amount of calories, but to two groups, and then one group eats a lot of times but very little, and the other one has normal meals but more spaced out. And so the number of calories is the same. What they found is that the people who are eating all the time but very little, they're always hungry, and they start even gaining weight. But if you do the intermittent fasting version, that group, they reported that hunger would eventually go away, and they have better health markers, and actually lost. They were just more fit. And so there's something about, I think this is speculation at this point, that because of our past as hunters and gatherers, like we somehow were brought up as eating seldom, and but then a lot at a time, which again, I'm not advocating for eating a lot at a time, but but still spacing more the meals. I think it's because that's just how we were brought up, and also it brings us back nicely to the whole insulin receptor story, right? Every time you eat, your body will be triggered to make insulin. And so you could imagine that having a constant insulin spiking is not the best for your health, is not the best for your longevity. So to me, it makes sense, at least intuitively, that if you limit the number of times that you have insulin spikes, you will prolong your lifespan, right? You can see it almost as a clock, like the clock is ticking every time you secrete insulin. And so there's something with it, because again, if you mess with the insulin receptor in all these different species, their longevity goes up, and calorie restriction, CR, right, is so far, one of the only proven methods to really increase lifespan, again, in animal models, and then people also report amazing results. And so I really believe there's something to be said about fasting. And then so how it works now inside your body, right, at the cellular level, at the other levels, I think that's an interesting question. It's going to be harder to address, I think in part because, in the laboratory, our cells are never hungry. We keep feeding them nutrients and everything. And so, but we can do, of course, fasting. You can experience where you also fast your cells in the laboratory, Look at stuff like mTOR pathway and others. People routinely starve cells either from nutrients or even from fetal bovine serum is an example of thing that we add to the medium to make it rich in nutrients. And so people do starving experiments. And so I think we, trying to understand how that impacts the health of the cells and also their fate. And, it turns out like gene regulation, epigenetics, is linked to metabolism. Because, the epigenetics, meaning on top of genetics, we have like DNA methylation, histone methylation, histone acetylation. These methyl and acetyl groups, they don't come from thin air. They come from what you eat. That's why they tell pregnant women to eat enough folic acid and all that stuff, because they need to have, all the genes expressed as, properly as they should, to put it very simple. And so, metabolism will also have an impact on epigenetics, which, controls gene regulation, so basically everything. So everything about the cell can be impacted about metabolism. So there's some work by Leonard Brent at MIT on the sirtuins. So that's yet another topic that, I don't work on it, but I know it exists. And so I just see more and more links, between insulin, intermittent fasting, sirtuins. That makes me believe that there's something there. And what's great is that everyone can do it. You can always, hopefully, maybe you have a very busy schedule, but otherwise, you can always eat less or eat less frequently. So that's actually a very nice intervention that does not need, you're doing less. Sometimes less is more. And so I think the restriction, intermittent fasting, is a good example of something that everyone can do it, or almost everyone can do it, and it can have visible effects.
Great explanation, and I completely agree with everything you just stated there. All the research that I've done basically lines up with what you just stated. So I was actually just thinking, because you mentioned Dr. George Church earlier at Harvard, the geneticist, and I've also brought up Dr. David Sinclair, and you just brought up sirtuins. Dr. David Sinclair is at Harvard as well, done a lot of research there. Do you have a relationship with either of them, being at Harvard, getting your PhD there? Have you met them, talked to them, worked with them at all?
Yeah, it's a good question. I think Harvard is a bubble, but also a big place at the same time. And so I've met George a couple times. I don't think you'd remember me, though, let's be honest. I've never met David, though, unfortunately. But, one of my lab mates right now, as of today, he works in George Church's lab as a PhD student. I mean, his lab, I think, has 50 people, I think. It's a very large operation. And, every time George gives a talk, there's this crazy animated site, all the companies that they help start, all the conflicts of interest. And so he's a very productive individual. He does really cool stuff. I have one of his books called Regenesis, which I think in the end is going to be a bit like you mentioned Aubrey de Grey's book, Standing the Test of Time, about aging. I think his book might do it as well, because this book called Regenesis by George Church, it was written before CRISPR was found to work very well in human cells. And yet the way it talks about things is like a post-CRISPR world. And so it's just funny how, the predictive power that, these people that do amazing, wide-ranging work have, it always, it's really interesting to me. Because he sees things for example, how amino acids are chiral, they mean that they're not the same as their mirror image. And so viruses exploit our receptors that are made of amino acids, right, proteins. And so you could imagine a crazy world where we reverse the orientation of our amino acids, so now viruses can no longer infect us. And so he has all these ideas in his book that was oh, interesting. No one ever told me about this. And so, we need, I think scientists don't usually have time to write books. So Aubrey, wrote one book and I was okay, this popular book, I need to give interviews and keep doing my research. And George Church, I'm sure same thing. He has papers to publish. He doesn't have time to write books. But it's almost a shame at the same time, again, that's why we need to live longer, because if they live longer, then they'll have less urgency for time, and they can actually write more books, so we can further increase our lifespan. So again, I think just having more people will result in having more scientists working on aging, so it keeps getting pushed more and more. Also, having more time will give these people more time to work on something that will give us even more time. So it's a positive feedback loop of something good, because we're talking about, I think, at least I talk about health span, it's a healthy years of living, it's not just being around, it's actually being healthy and being able to enjoy life and, satisfy curiosity and, write more books. George has to write more books, David has to write more books. It's a crime they don't have more time to write more books. So yes, I don't have any close contact with them, but I know both of them as scientists, that is. And so, I hope them and more like them continue to really push forward in all these sorts of important questions.
Definitely. And one thing that you mentioned there, talking about if we live longer, then they'll have more time to help us live even longer. So Aubrey de Grey coined this term about 20 years ago. I think it was 2001 or so, longevity escape velocity. So for those who aren't familiar with that term, it basically describes that. So we will have reached longevity escape velocity when science is adding more than 1 year to your life, even if it's just 1 year and 1 day, if they're adding more than 1 year to the human life expectancy in every year. So therefore, it's like another year ticks by chronologically. We're all a chronologically year older. However, we've learned how to reverse aging by 1 year and 1 day. That's when we've reached longevity escape velocity. But, one thing that I also want to bring up is that just because something is possible, it doesn't mean that it is available for everybody from an economic and governmental standpoint. So those are things that we have to consider as well, too. I'm a big proponent and believer that we need to make these technologies available for everybody, not just the super elite. But I'm also a free market capitalist guy. I truly, truly believe in the free market, and I feel like I feel like I'm in a small group at this point. Socialism seems to be taking over so much on our planet, and the free market is so important. So just a real quick plug for people. I recommend you read the free book online. You can Google it. It's written in 1946 by Henry Hazlitt. It's called Economics in One Lesson. So it's very, very simple. And I highly recommend, if you don't know much about economics, or if you think you know a lot about economics, just read this one book, and it might actually change your perception on things and show you that the free market is super important. So just a little quick rant from me there on free market capitalism. But just getting back to David Sinclair and longevity, escape velocity, and all those things, I think this is a really important concept, and I love the work that David Sinclair and Dr. George Church are doing, and the Harvard background. Their Harvard stamp there gives them so much credibility, just like yours as well too. So we need more people from Harvard, from Stanford, and these prestigious institutions, and the big Silicon Valley companies like Apple, Google. We need these big companies starting to talk about reversing aging more. Jeff Bezos, the wealthiest person on the planet, the founder and CEO of Amazon, he invested millions of dollars into Unity Biotechnology a few years ago, a cellular senescence company, a senolytics company. Technically, they're trying to end cellular senescence. These things are really important, but they're still not very well known. Mark Zuckerberg, the founder and CEO of Facebook, he has started the Chan Zuckerberg Initiative with his wife, Priscilla Chan. She's a medical doctor, and their stated goal is to end all diseases by the year 2100, which is only 80 years from right now. I know Warren Buffett is trying to reverse aging. He's researching it and interested in it. I know a lot of people aren't aware of that, but Dr. Peter Attia runs an anti-aging practice in New York. It looks like, Leo, you know who he is. He has his own podcast. Definitely subscribe to his YouTube channel. Follow him on Instagram, Twitter, all that. I saw him, Peter Attia, in a podcast in 2018 state that one of his patients, who's an elderly man in his 80s or so, who's been friends with Warren Buffett for decades, said that Warren Buffett would see him every 6 months or so, and he'd always be interested in a business opportunity for decades. But over the last couple of years, so this would be 2016 to 2018, whenever Warren Buffett saw his friend, all he would want to talk about is basically anti-aging. So Warren Buffett is doing this secretly, yet Warren Buffett has like $90 billion. We just need Warren Buffett to invest, like 1 billion of that, right? It could totally change this landscape. So Leo, I could go on and on and on with this research that I've done about like billionaires and who are interested in anti-aging and how we can change things. Peter Thiel is obviously very interested, but he's only got maybe $3 or $4 billion. It's kind of funny to say only got $3 or $4 billion, right? But compared to these mega billionaires, right? The co-founders of Google, Sergey Brin and Larry Page, they founded Calico back in 2014, I believe. And Calico has been basically a big nothing burger as of right now. According to Aubrey de Grey and myself, I've been to Calico in South San Francisco. They were on my account list when I was selling corporate enterprise e-learning at LinkedIn in 2017. And I went there, met with their HR team, tried to learn more about it. They wouldn't share anything. They haven't shared anything publicly. So I know I've been talking a lot here, Leo. The question, for you that I'm presenting is, how do we get, investment into your lab and labs like yours? And I'm not talking about like, $1 million here or there. I'm talking about the big money, the multi-billions dollars, because we know that governments are in debt, and we know that you guys have to work so hard to get grant money and stuff like that. How do we get private investors, who are the ones who have all the money, these very wealthy people, to start donating or investing in technologies and companies, and universities like UCSF to support your work? What are your ideas on this stuff, Leo?
Yeah, I think it's really boils down to communication. Like really make them understand, if they don't already, that this is such an important problem, and that you will have very direct benefits to them and their family and friends and everyone in the world. I mean, again, there are so many problems that stem from aging, that by targeting aging, you actually target many things at once. And so I think that makes it a very interesting problem to solve. Right, because as I mentioned, like you said, like 95% of the funding from the National Institute of Aging goes to Alzheimer's disease. Well, what if you only make it only 50%? There already be an improvement, and that already sounds bad that half of the funding will go just to one disease if it's the Institute of Aging. And so to make understand also, like no matter how much money you have, that's not going to prevent you from getting old like everyone else. Maybe you have more money to like eat better, do a lot of plastic surgery, but it's not going to prevent the actual aging inside you that much, And so I think it will be in their direct interest again to invest in that kind of stuff. And again, I think the ramifications, every time you do science, you always discover things that you're not expecting to. So like a lot of positives, I think NASA, for example, all their research, that's why I have credit cards, that's why I have all sorts of like cool technologies that were like just, side things, just like no one cared about it. And look, how much they've helped our way of living. And so I think likewise, by investing more in aging, you could learn about so many aspects of biology. So that's from a science perspective, and then from maybe like from like a billionaire perspective, is really just like how you're helping people, helping yourself, your community. Like if you're 70 or 80 years old, maybe it's about time you think about aging, right? To be very honest. And so I think a lot can be done even in 5 years. Because now we have so many powerful, we generate so much data, we can analyze it all. Like we can sequence whole genomes, from human, like 3 billion bases, 3 billion letters. We can sequence so many of those every day. We don't even have time to look at all of it. And so, but if we had more people working on it, then we would, So I think, again, as I said, it doesn't seem like rocket science to me. I think it's just a matter of like throwing more people, more talent, more money at it, and then you'll get results faster. Some things can intrinsically be accelerated, right? I cannot change how fast a cell divides, or how long does it take for a mouse to be, born. But what you can change is how many people are doing that at the same time in different aspects of it. And then, again, there's so many facets to be addressed that we didn't even mention. Autophagy, for example. The way that cells recycle stuff inside themselves. That's yet another facet that has to be explored further, right? Because if you can activate, autophagy just enough, the right amount, your cells themselves will live longer. And especially important for the adult stem cells because they live longer, so they have more time to accumulate damage. So we need to really make sure those cells stay as pristine as possible. So autophagy is another example that might actually be linked to the caloric restriction part of it. But so, there's just so many. So there's just so many facets that just need more people doing them and just doing more of it. Because sometimes people are interested in it, but then they don't go into it because there's no opportunities. Like you imagine, one challenge that exists, so there's lack of funding, also the time, like to study aging, it almost, it's probably going to take longer than studying other stuff. Like if you study cancer, I have models where the cancer will, come to the end stage in like weeks. But how to study aging in weeks? You have to be very smart about it. Like maybe you study autophagy, you can have experiments that only take weeks. Or if you study caloric restriction, but then if you study it more globally, then it takes years. Like the mouse lives for 2 years. So how long does it take to prove that the mouse can live for 3 years now? Well, 3 years. So, so that's something that maybe discourages some people from going into it. But that discouragement could be overcome with enough money and incentive. Because now I feel like, okay, we understand this research takes longer than usual, but we understand that. So we're going to give you more money and longer grants. So right now, R01, which is NIH bread and butter for principal investigators, is like 5 years. Well, can we give grants that last for 10 years instead? So you also have some, security, some safety that what you're working on, is not going to get cut off. That's so important. I mean, I feel like that's, I think, maybe a big difference between, old-time science and nowadays science is that previously people had the time. There was not as much pressure like, oh, if I don't publish this paper next year, then I don't get the grant for the year after. And so this is yet another discussion, but like how you can't do fast food science always, So, and I think for aging especially, you can't really, some things you really have to just wait. To demonstrate that the mouse lives 3 years, you have to wait at least 3 years. And so there's no way around it. And so you just have to somehow, I don't have all the answers, but you have to somehow change the incentive system and the funding mechanisms to make that more possible. Otherwise, no one's going to go into it. They're like, well, I also have a family and kids and a life to live. And so, so in the end, I think people, they'll be, scared from it. So there's different levels. Some people don't want to talk about it. Some people talk about it, but don't want to work on it. And some people want to work on it, but they can't for all sorts of reasons that, again, I think many of them, we could fix them just with more funding and different timing of the grants. Again, non-science stuff. But that could help tremendously because now I feel like, okay, we understand that we're not going to give me anything interesting before 3 years from now. I mean, I understand it. And 3 years ago in the fly, I mean, I've been here for 4 years. So time kind of flies, especially when you do what you love. And so I think it's totally feasible. It's just a matter of money and new funding mechanisms. And so now you have more people that are like, oh yeah, this is really fascinating. And so instead of in 5 years, you're having 3 papers, because you have to have 3 papers, right? Otherwise you don't survive, publish or perish. How about you just have 1 paper, but it really moves the needle in the field of aging, right? That'll be more significant. I mean, Newton wrote 1 big book, or like Einstein, they didn't have 500 papers. I mean, I know it sounds a bad thing to have 500 papers, but I'm just saying, I think we have to take a step back to take 2 steps forward. And so, yeah, just try to, create environments that motivate more people to go into aging research, into stem cell research. It takes more money and more time than other types of research, but it should also be that much more interesting, that much more impactful.
Very well said. So you just stated there sometimes you have to take 1 step backwards to take 2 steps forwards. And I believe that's something along the lines of Recharge Biomedical's phrase or saying as well too, Dr. Ed Park's anti-aging company in Orange County. All right, Leo, can you tell me a little bit about Immunodietica?
Oh yeah, of course. And so the idea behind this company, and really it's almost a new field of study, is to understand the interaction between diet, what we eat, and autoimmune disease. And so what that means is that I think, as I mentioned before, when an autoimmune disease, could be multiple sclerosis, type 1 diabetes, it's the immune system that is attacking tissues on your own body. It's like the body at war with itself. And so it seems what's not clear is how does it start, and how are the symptoms and the severity modulated. So, we have people, again, if you look at twin studies, sometimes the agreement between twins is like 30%, 20%, so very low. And these people have the same exact genome. So there must be something else to it. And so there's a few theories out there. So one of them, would be that there's some event that triggers a disease, and that event is the environment, right? It's not the genetics. And so, for example, viral infections, in some cases, have been implicated in autoimmune disease. And we know from both mouse and humans that there's this interesting process called molecular mimicry. What that means is that you have peptides, so the pieces of proteins that get presented on the HLA molecules, that are shared between a virus or a bacterium and our cells. So, for example, there's a study showing that if you have a certain type of bacteria in your microbiome, in the mouse, they have a protein peptide that matches a peptide present in a protein found in heart cells. And so then you can trigger this mice to have autoimmune disease called myocarditis. So the target is the heart cells. You can trigger it through the gut. And so what that means is that you can trigger an autoimmune disease by manipulating the environment. And likewise, the corollary, the implication is that you can also avoid disease, or you can make it better, also by changing the environment. So that's how Immunodietica started. Was me and my colleague, I was at Gerstein. We were thinking about this, and so even though most of my time is spent working with cells and gene therapy using cells, sometimes you also need to look for simpler solutions or other examples of things that we can do. And so diet, again, it's one of the easiest ways we can modulate, our body works in our day-to-day life. And so what we've been doing is we've been trying to make sense out of all these observations that food has an impact on both the severity and also the incidence of autoimmune disease. There's, for example, old studies showing that if you were to plot milk consumption versus multiple sclerosis incidence, they go hand in hand. Now, why that happens is not clear. And what's interesting also, I should say, is that the same study that looked at cheese, and that correlation does not exist. So something in raw milk that would somehow be associated with multiple sclerosis incidence. And then there's other reports of people who have, for example, rheumatoid arthritis, RA, so the disease of the joints, inflammation in the joints, autoimmune characteristics, that they say that their symptoms get better or worse depending on what they eat. And indeed, there's this clinical trial in the 90s where if people go fully vegetarian for a year, their symptoms get much better. So morning stiffness, joint pain, etc. And so we know that food, what you eat, can really interact with the state of your immune system in general, and in particular for autoimmune disorders. So that's what Immunodietica really is trying to do, is trying to map what is the mechanism behind these effects. And so one thing we've done is, we now, it's 2020, have access to many, a lot of data. And so what we do know is we know the complete genomes and proteomes, all the proteins, from many organisms that we usually consume as food. We have the pig and the cow and the sheep and the celery and the rice. And so we take those and then we map into those epitopes, peptides, that have been implicated in autoimmune disease. So multiple sclerosis, for example, has 2,000 epitopes derived mostly from proteins found in the nervous system, as expected. And then you take those, those protein epitopes and you map them against the proteomes of animals and plants. And so by doing that, we basically have a map, we have a matrix where we can see each animal, each food source, how risky or less risky could it be for someone with a certain disease. So, for example, for multiple sclerosis, we'll find, we'll find hundreds actually of peptides that are found in animal proteins that would be the same exact ones that we have and that have been found to be the targets of this disease. And so you could imagine now, if you have a patient with a certain disease, we could recommend them not to eat a meat of a certain animal or a certain food product. And so what we found, we've had 2 publications now. Well, one of them is not published yet, it's been accepted, but it's already on bioRxiv, so everyone can read at least the beginnings of it. And so what we find, for example, if you compare across all animals that we usually consume and then look for unique epitopes, the pig really stands out. I don't know why, we don't know why, but somehow there's hundreds of peptide epitopes that are found in pig proteins. They're not found in cow or in rabbits or in sheep or in goats. So animals that, if you look from genetic standpoint, they're more or less the same evolutionary distance from us than the pig is. They're all red meats, right? So they're all red meats. They're all mammals. And yet, for some reason, this one stands out. So we're trying to understand why that is. And then number 2 is we've actually gone one step further, which is to make it personalized. So because of different HLA alleles, this has an impact, not just in organ transplant rejection, but there's also good things about it. And so one thing is that each HLA allele will present different peptides. And so peptides that would be dangerous to you, if you will not be dangerous to me, and vice versa. So from all this information, it will have an impact on people's lives potentially, if and only if we can match that up with their specific genetic makeup. So now what we've developed is what we call a sensitivity passport, where we have your HLA sequences, your HLA alleles, and we can run these peptides against those HLAs, and we can predict which ones bind, which ones don't. There's algorithms. So we've eluded so many peptides from HLAs that we know if a peptide will bind or not with some level of certainty. And so with this sensitivity passport, we can really say, okay, for this specific person, these are the things that he or she should look at. And so that's where we are right now. We're now expanding by also including food proteomics. So you can do mass spectrometry of a piece of bacon or milk or egg. And so we're trying to put that in. So we talk not just about pig, but actually talk about bacon. We don't just talk about cow. We actually talk about milk. We just talk about chicken, but also about chicken breast versus egg yolk versus egg white. So that's where we are right now. We're really expanding our database, basically, number one. And number two, making more and more personalized. So the HLA is the first step, obviously. Another step will be the microbiome. As I mentioned, different microbes can really modulate or even cause autoimmune disease. It is thought and been demonstrated in the mouse, first and foremost. They're just easier to work with than humans. But so we think that, as we keep adding layers to this database, we can hopefully, make sense of how diet can influence autoimmune disease and also help individuals. Because again, for rheumatoid arthritis, for example, people, they'll do anything to have their symptoms go away. And so if we can help these people, there'll be a big difference. And, there's almost 50 million people in the United States that have some form of autoimmune disease. And so this could help millions of people. And again, it's a disease that there's no cure. There's no cure for autoimmune disorders like multiple sclerosis. I mean, there's some drugs that help you with it, but they don't actually fix the problem. Now, for my other line of work, maybe if you can give these people engineered regulatory T cells, we'll fix the problem. But until we get there, I hope instead of 10, 20 years, I hope that this work that I'm involved in Immunodietica will be years, not decades, until we can really help people with it.
Wow, that is just super fascinating, Leo. And you're just an incredible person. All the things that you're working on is so incredible. I didn't catch fully what you said about the pig. So what is the net of that for the pig? Does that mean that it's bad for humans to eat pigs?
Right. So I think what this means is that somehow if you were to pick an animal to stop eating, pig is a prime candidate, because that's just the way you'll avoid most or the most autoimmune epitopes. Also, I should say some work not by me showing that there's some sugars, saccharides that are found in pork, in pig, but not in us. And so what's weird is that when we consume this meat, these sugars get integrated in our proteins. And then they're not exactly like ours. And so we get what's called xeno-autoantibodies. So it's almost like an oxymoron, because xeno is foreign and auto is yourself. So how can an antibody be xeno and auto at the same time? And that's possible because xeno because from the pig, and auto because against your own protein. So somehow the accumulation of this stuff over time, over years perhaps, will create some low-grade inflammation. And then if you remember the signal 1, signal 2, we have the danger signal, the signal 2. And so over time, it is antibodies building up that can lead to inflammation. And so maybe, just maybe, a link between red meat consumption, probably especially processed red meat, because if you look over time, the consumption of red meat has not changed or even gone slightly down, but the consumption of processed meat has gone up over the years, which I think is problematic because, who knows what they put in it. I think like food additives have definitely been shown to be, to cause trouble in your immune system and so on and so forth. And so just to say that, these are different ways in which we kind of knew here and there that diet has an impact on autoimmune disease. And again, especially pig, I don't know why. That's, again, is an observation. We didn't get to the mechanism yet. But it's very black and white. If you look at our publication, you see, it's a heat map where, the darker it is, the more autoimmune peptide content is there. And, the pig is, very dark spot across all the other animals and plants that we looked at.
Very fascinating. So I know my cousins and family in Israel, they are Orthodox Jews and they don't eat pig. And I know there's many cultures that just don't eat pig. So maybe I will adopt their habits. So I assume you don't eat pork at all?
It's very rare, yeah. And so that's interesting. So since you mentioned the Jewish and others actually looking at, so what I thought was, well, if it really is that this makes a difference, then you should see an impact in human evolution over the thousands of years at least. Because HLAs, again, if you look at different populations, let's say the Jewish population versus Chinese, Han-Chinese versus others, you see different HLAs popping up. I mean, this is how when you see a paper about, they know this certain population, traveled the world and migrated, they follow them based on HLA sequencing, because different HLA alleles mark different, ethnic groups. And so I thought, well, if this really has a difference, then if I look at HLAs most prevalent in the Jewish population, which doesn't eat pork, right? It's in their book from like thousands of years ago. Don't eat pork, don't even touch it. Compared with, say, Chinese population, where they eat a lot of pork. I mean, so much so that I don't speak Chinese myself, disclaimer, but I have many friends who do. And so apparently the Chinese character for meat has a Chinese character for pig contained in it. And so pork meat is so ingrained in the Chinese culture that literally the symbol for meat is basically pig with some extra things in it. And so if you compare these two, polar opposites, you might see a difference in binding to their HLAs from the unique pig epitopes, right? And indeed, I saw that difference. That's not published yet, but working on it. Like you see, statistically significant differences, p less than 0.01, whatever it is, the cutoff. But more importantly, it doesn't matter in biology, right? And so that's what, again, we're trying to get in touch with epidemiologists, actually, and human geneticists to like expand this observation. Because, I think science, part of what makes it fun is that none of us knows everything. But hopefully we have friends or people that do, collectively, obviously. And so I'm looking forward, in this case for Immunodietica, and in general, obviously, to work with other people on these type of problems that I alone cannot tackle. But I would love to.
I love it. And tying this all together, I mentioned longevity escape velocity. I'm the co-founder of a company called LEV Sciences, which, stands for longevity escape velocity. Vladimir Trofanov is my co-founder, and it's a social media platform for longevity. So Leo, I'll include the link in the description below, and you can check the timestamps if you're watching. Please create a profile. It's completely free. And we want people to just input their data, and we don't know exactly what the website is going to turn into. We have all sorts of different aspirations, but we want it to be a social component. We want you to put your data in there. We want it to be networking as well too. It's easy to find people. You and I found each other on Facebook, on LinkedIn. We already talked about, follow Leo on social media, Twitter, Instagram. But this is going to be a specifically focused longevity social media platform. So what that means is that you can actually put in a lot of your biomarker information, and then you can put in, your lifestyle, what you're doing, things you might, vitamins, supplements, nutrients, drugs you might be taking, treatments you might have done, like if you've done stem cell injections or exosomes, and then just talk about what's happened, because we can't just expect the old model, academia and stuff to just be doing all these clinical trials. We need to take control in a decentralized manner as individuals to do the best documenting our things. And it might not be as well documented as it could be in a clinical trial with certain settings, but anecdotes is better than nothing, in my opinion. And so we want to go further from just anecdotes. We want people to have their biomarker tests in there. So that's essentially what this is. And I think that it's really important for us to solve the aging problem, to have some type of a network like this. And another thing that I heard you mention was about the microbiome, Leo. I don't know if you had a chance to see it yet, but last night my longevity team on June 23rd live streamed with the founder and CEO and billionaire of Viome, Naveen Jain. And man, that guy is just so fascinating. I've watched so much of his content over the years, like literally hundreds of hours of videos of him on YouTube. And he repeats some of the same stuff every now and then, which, like I do, that's not a negative. It's actually a positive, because Naveen, it repeats the important things. But man, he just brings so much new material. He's a wealth of information. So, what do you know about Viome, and do you have any aspirations? It seems to me like it could be a good company for you to partner with there. We're talking about to me, they're the leaders in the microbiome research when it comes to actually having patient information. What do you know about Viome, Leo?
Yeah, no, I definitely heard of it. I think it's very important work. And so it's interesting because, if you think about our body, we have human cells, obviously, but also have a lot of bacterial cells. And so it only makes sense to start exploring those. And also, like if you think about it, like it's probably easier to manipulate a bacterial cell than a human cell. And so I think, when you talk about cell therapy, you could maybe somehow put in bacteria in that category because, like in your gut, a lot of metabolites, they come not from your cells, but from your guests, from the bacteria in your microbiome. And there's also been some very interesting results from fecal transplants and microbiome. And so I think it's a almost untapped resource. Like we need to do more of the microbiome. We need to, like everyone is different. So I think there's still some work to do in understanding, like what's good for one person might not be good for another person. So I think there's some work to be done there because we're all so different. But, again, it's a totally surpassable problem. We just need to keep getting the data and looking at the data. And again, we know from more precise, more restricted systems that, certain microbes do more defined things that we can, benefit from. We've seen microbes that secrete molecules that, they can turn immune response a certain way. And actually in cancer immunotherapy, of all examples, you see that the microbiome can determine whether the therapy works or not. So wouldn't it be nice to know beforehand if it's worth spending $500,000 with that treatment? And so even again, pure economic, if you will, I think so in the microbiome has the potential to multiply. The return on investment would be huge because by knowing this about the microbiome, we can predict a lot more than, like what you get out is much more than what you put in. And so, responsive therapy could be helpful to predict using microbiome and also in healthy people, obviously. And so again, like you'll get interviewed because what you eat also changes your microbiome. I mean, like when you travel, you might get upset because your microbiome is not used to these new foods and spices. And so that could be interesting too. I mean, can I somehow, when I travel, can I somehow get a sample of the microbiome? And so when I eat, I don't get as sick or not get sick at all. And so there's a lot of usages, some more mundane than others that could be taken from studying the microbiome.
Yeah, definitely. I can just say for myself that I did my microbiome test through Viome, my wife and I, in March 2019. And I did a video about it on YouTube describing the kit and what it's like. They take a little sample of your poo, and then you have the app. And I got the app here on my phone. Here's my Viome here. And it tells me what foods to eat and what foods to avoid, what foods are my superfoods and what foods are just foods for me to be eating. And I've been following this diet for over a year, and I strongly believe that it has improved my health. Without getting too detailed, basically my GI tract is much like it was when I was younger. My number twos come out smoother, fuller. I just feel like in general healthier. So I don't think that could just be explained with placebo. And I think, even Naveen Jain says this, that we're still in the very beginning of understanding the microbiome. It's very new evolving science, but I think that they are leading it with their, machine learning and their algorithms, their AI algorithms, and they're learning a lot. And the more customers they get, the more data they're going to have to learn even more. So I purchased a kit for my mom and my mother-in-law for Mother's Day last year. I said my wife has it. I've encouraged other people to do it. I probably need to get retested as well too. They have a new health intelligence test as well too now. The gut intelligence test is the one that I've referred to where they test your poo, but now they're also testing your blood and your saliva, and they have aspirations to test your skin and every single part of the microbiome of the body. So I think it's super important. And Naveen Jain is not he's not vague about it at all. He says that they are trying to make chronic illness optional through the microbiome. It might be that powerful. That's what's so crazy about solving the aging problem, is that we still don't know enough. It could be as simple as, having very, very personalized diet based off your microbiome to slow, stop, and maybe even reverse some of these chronic conditions and maybe even aging itself. I think that time will just tell as this technology evolves and as we see. But check out our live stream from last night. I'll put a card there with Naveen Jain. We were very appreciative to have him on the show. He's a very, very fascinating guy on so many different levels. So did you get a chance to watch that yet, Leo, or did you even?
Yeah, I've watched it fully, like I started. So, no, and again, I've heard of the company before, so I was obviously curious. I just hadn't finished it yet. But so, yeah, I think even for us, I think in general, there's a few problems that, I feel like I went to an autoimmune disease or autoimmune disease patients to the group of people that can benefit from them. For example, organ transplant, usually you think about it as like the person's immune system is normal, but the organ is failing, and then you put a new organ in. An autoimmune disease patient has an additional problem, which is even if you put a brand new organ in, it will be like doing a sandcastle by the ocean, because the immune system comes and kills the whole thing again.
Right.
So if we can expand regenerative medicine to help those people. And so I think likewise for these problems of diet, and I think the chronic disease, which many autoimmune diseases come out to be chronic, like type 1 diabetes now, if you inject your insulin every day, it's now a chronic condition. You no longer usually die from it. But so, yeah, it'll be definitely interesting to reach out to him or others, because I think, again, it will be kind of a new layer, so you have the microbiome, and you have these other aspects. And then if you also have the immunological aspect of it, so like the peptide composition, or the I guess, the endogenic properties of different foods, which will, again, differ between people because of different HLAs, with different microbiomes, right? So maybe it interacts differently depending on your microbiome. And so all these things, I think, will be valuable to just, we mentioned microbiome, saliva, blood, could be interesting to add yet more layers to this. And so going, I guess, to be another point ago, we mentioned that try to have like a decentralized system where people share their data, how you feel, your biomarker levels. I think that's a very powerful idea because, data is data. And so in the end, when you do a trial or an experiment in the laboratory, what you want is to have enough data points done in similar ways that you can make a conclusion out of them. Now, whether those data points come all in the same week or they come over the course of years from different people, in theory, that should make that big of a difference. Okay, if it's a robust effect, it should be very obvious, right? And so I think that could be very valuable to acquire that data, keep acquiring it. And then over time, the value will keep adding. It will be an added value. Because every time it's like, we could make a conclusion based on 20 people, 50 people, 100 people, 1,000 people. So your numbers will keep growing. So I think it will be rewarding. Over time, you can dig deeper into it because you can see even small and smaller effects. About GWAS, like the Genome-Wide Association studies, they can see crazy stuff because there's so many people, right? They need 5,000 patients, 5,000 healthy controls, and then they can see something. Sometimes they need 10,000 each. So these are huge numbers. In the laboratory, like n equals 3 and it's done. But when it's like genetics of people, it's like tens of thousands of people. And so these are tiny effects. And so some people will be like, well, this effect is so small, it doesn't really make a difference. But what they seem to forget is that it's small in this context. If you actually are to, instead of doing that slight polymorphism, if you say get rid of the whole gene, you now get the black and white phenotype, which is what people always like. You like to hit things with a hammer and see something black and white. And so by using 20,000 people, you're able to find the needle in the haystack. You found the gene marked by that polymorphism that changed your height by 0.1%. But now if you delete the gene or add the gene, you have a dramatic effect. And so I think that's very powerful for, not so much for height maybe, but for diseases, for type 1 diabetes, for example. What is it that is driving it? What gene should we target when we do therapies? Because if I'm adding cells and I can modify those cells, can I do it the best possible way? And so maybe these patients need a certain gene with a higher function, or maybe they need other gene to be done with it. So while I'm adding cells, I might as well make them the best possible cells. And so these studies that look at tiny effects with many people, their benefits can then be large. I'm part of a study, it got published in Cell last year, where we narrowed down on the GPCR, so a G protein coupled receptor, 146, that it was found in GWAS to be associated with lipids, with lipid levels, which are a risk factor for heart disease. So okay, maybe we should look into that. Again, small effect, it's from humans though, so it might be important. And then indeed, If you do in pluripotent stem cells that became fat and liver, or in mice, when you knock out the gene in mice, you can feed the mice as much fat as you want. They don't get atherosclerosis. So by a small hint, we could have now a very powerful drug target. Because actually, so the most best-selling drug in the world, statins, target the GPCR. So this GPCR is a class of molecules that is very druggable, is very targetable. And so it's just an example of how a small hint, needle in the haystack, if you have like the right system. And so I think likewise the microbiome, like small tweaks might seem small, but it can have like a huge effect in the individual.
Definitely. Wow, really great examples there. And you mentioned earlier about, traveling and what it could have effect on your microbiome and your body in general, from the food. So yeah, maybe for LEV Sciences, we'll encourage people to put in, where they've traveled and things. Because I know I've been over 40 countries, and my wife and I went to 25 countries in 2018 alone. We quit our jobs, sold our home, and decided to travel in 2018. So I did wonder about that. I was researching the microbiome as I was doing that and wondering like, oh, and that's what's so cool about traveling, the different cultures. We were actually in Portugal just at the airport, but the different foods, the different cultures, that's the beauty of traveling, and just wondering like all sorts of different types of foods and things that I'd never even heard of that I ingested. And I was just wondered like, yes, well, I wonder if there's something in here in my microbiome in my body is like experiencing for the first time. So that's something that we can maybe incorporate in the website as well too. I'll talk with Vladimir about that. So Leo, one other thing that I really wanted to touch upon was, I talked about MCell in Kiev, Ukraine, the fetal stem cell company. Talked about Dream Body Clinic that I went to in Nuevo Vallarta, Mexico. Talked about STEM Aid in Cabo, Baja, Mexico, where they're doing the pluripotent stem cells. There's another company that is, pretty famous. It is Dr. Neil Reardon's company. It's called Stem Cell Institute. They're in Panama. And Dr. Neil Reardon was on the Joe Rogan podcast a little over 2 years ago in early 2018. And he was on there with Mel Gibson, the famous actor. And Mel Gibson talked about how his dad, Hutton Gibson, which last time I Googled and looked at his Wikipedia, he's still alive. He's like 101 years old. Maybe 9 years ago or so. So we're talking maybe 2011-ish, based off my memory. Hutton Gibson was on death's doorstep. Mel took him to all the best doctors, the best clinics in America, and they all pretty much told him that there's nothing we can do. So Mel, being in Hollywood and being Mel Gibson and being worth, over $100 million and being, a famous Hollywood celebrity, he heard through some celebrity friends of his about this clinic, Stem Cell Institute in Panama. And at first Mel was kind of like, yeah, whatever, stem cells, like, why wouldn't I know about this if this was like real? So but then he thought, what do I have to lose? So Mel took his dad, Hutton Gibson, in a wheelchair all the way down to Panama. And based off what Neil Reardon said, Hutton Gibson was in his wheelchair and he was basically done. He could hardly talk. He was almost dead, apparently. And let's just say Hutton Gibson has had many mesenchymal stem cell injections over the years, and he's still alive today. So these are just like the ones that I had injected in Mexico. These are derived from the Wharton's jelly, which has a lot of mesenchymal stem cells, which the Wharton's jelly is a specific part of the umbilical cord from a healthy birth. And I would just love for people to research this. The reason why I didn't go to Panama, the Stem Cell Institute, is because their costs are just way higher than Dream Body Clinic in Mexico. So, money is a big thing that we haven't talked enough about in here. That's why I didn't go to any place in America. They do offer mesenchymal stem cells at some clinics in America, but they're autologous, which, as Leo and I have talked about, autologous means it's from your own body. So they'll like extract it from your adipose fat, your belly fat, or they'll extract it from your bone marrow. They'll replicate them and then they'll inject them like into your ankle if you're having an ankle problem, for example. They'll do that in America, but we know that those cells are old. If they did it for me, they'd be taking my 35-year-old cells and then injecting them in. Whereas I had, day zero from an umbilical cord, which we know from the theory of aging, cellular aging, that we age because our cells age, in its most basic form. We're about 40 trillion cells is about what the human body is made up of. And as those cells age, we age. So in general, what I'm trying to say here is that check the timestamp here. If you haven't watched this Joe Rogan interview with Neil Reardon, I highly suggest you check it out. Because there's a lot of celebrities that have gone there now. I've interviewed Roger Ver, very famous Bitcoin pioneer, and he went there for an ACL tear in his knee in 2018, and his knee's better now. I interviewed him. I asked him, "Hey, do you think that the stem cells helped your knee?" And he said, "Well, I don't know. All I know is my knee's better. I don't know if it just got better normally or if the stem cells helped." But I've personally done enough research here, and what I said alone about Hutton Gibson, to think that they're definitely working. There's people, he's written a book. I have the book over here. He's written 2 books. I've read both of Neil Reardon's books. And chapter 6 in his book, Stem Cells: A Rising Tide, talks about people with, debilitating spinal injuries where they cannot walk. And then he's given them injections and now they're walking. So I guess, Leo, what's so crazy is that these things are happening, but they're not being reported well enough, by the mainstream media and our governments. Whereas that's what's so hard for so many people to believe this stuff, because your natural, at least my natural inclination, when I hear these things, I'm like, well, this must be a scam, or else I should have already heard of this. But that's really just not the case. These things actually are happening. They're just not being reported. So I just talked a whole lot there, Leo. Leo, you can reply in any way you want, but like in general, what can we do? What can you do? What can all of us do to get this message out to a bigger audience that stem cells are real, and that people like you are working on them, and that you need more funding? What can we do?
Yeah, no, I think again it's a general feeling that somehow there's just not enough of it getting out there. I mean, the less these things are talked about, the less transparent they will be, the less you'll learn from them. So everyone loses in this game. And so the fact that I have to go to Panama or to Mexico, that shouldn't be the case, because if this technology really does exist and has produced results, then we should have it too. And I mean, so much stem cell research happens in the United States. I mean, it's one of number 1 in the world.
That's the irony of all this, that it's all happening in America. It's kind of started here, but I think it was really the Bush administration roughly 15, 20 years ago in America that defunded a lot of this stuff. So a lot of the research went other places, to Germany, to Israel, to Kiev, Ukraine, Mexico, Panama, and many other places too. And now, the entrepreneurs have started businesses there. And I should mention this: Roger Ver, who I just mentioned, he's now working with Neil Reardon. He's now invested, because he's very wealthy from Bitcoin and other things. He's invested in a new stem cell company in Antigua, on one of the islands of the Caribbean. So I'm in touch with Roger there, and you know what? Maybe I should put you in touch with Roger, to maybe be an advisor for them, or get involved in some way, because this is from an investment entrepreneurial business standpoint. Here's another one. It's stem cell clinic being built in Antigua. Why isn't this being built in San Francisco? Why isn't this being built in New York, Kansas City, Austin, Texas, Miami, Florida? And it has to do with the regulations from my research. The FDA will not even allow us to replicate allogeneic stem cells. I talked about earlier autologous, which means from your own body. They will allow you to replicate those, but they will not allow the replication of the allogeneic stem cells. And so what that does from a purely economic standpoint is, I looked into clinics in America, chiropractors who inject previously frozen, cryogenically frozen umbilical cord derived Wharton's jelly stem cells, and basically I could get like 1 million or 2 million of the mesenchymal stem cells for like 4, 5, 6 grand, whereas I got like 300 million for 10 grand. So that's the true, like, at least in 2018, that's what I found from my research, and I believe it's still pretty much the same case now. So this is an FDA like regulation problem, as we've talked about here, where we might regulate ourselves out of like being competitive, in this. So what do you think about that?
I think we just need to have, and I think the administration tried to do something about like expediting review for certain trials for certain drugs, and so I don't know how that ended up panning out. But just the idea that you might be able to categorize trials in different groups, and have some of them go faster than others. Again, in Japan, that's exactly. I mean, I'm not making anything up. In Japan, it's exactly what they did. Like these stem cell therapies for the retinal degeneration and for heart and for Alzheimer's, I believe, for some neurodegenerative disease, they got this breakthrough designation, and so they were approved faster, and now they're doing them. Now, of course, some critics are say, well, then you might pay for it later or not. I mean, I don't know. I think they're doing it right now, and they'll know the results. And I think in the end, if everyone is an adult and agrees to it, and the data is being collected and being, published in journals and on the press everywhere, I mean, I think a good scenario, right? Because it's as open as possible. It's through the traditional legitimate channels, and there's no hidden things. There's no like, well, he said, she said, or I heard this, but then it's not published anywhere. I don't know anyone else that does this. And so it didn't have to be that way. I think we could do better than that. We could set up, instead of just saying no, can we say yes, but with less people, or show me this or that first? I think there has to be some middle ground between just like, stopping it from happening and just letting it all go right away. You also don't want that because also people's lives are at risk. Of course, I mean, stem cells are very powerful. You could imagine if you inject the wrong type of stem cells or at the wrong time. So we have that to take into consideration. But again, they went through all the review. I mean, the fact that they submitted and they looked at it, they know exactly what's being done. And then that it's not being I cannot believe that of like 100, all of them were so wrong that they couldn't go through. For 100 is just an hypothetical number, right? But just so it cannot be 0% of them. And again, an example from Regeneron that I knew from I think a decade ago. I mean, how come that didn't go through? Some encouraging results. And I think you mentioned spinal cord injury. Again, I've never injected stem cells in a person myself. I'm not a physician. I'm a PhD. I'm a scientist. But this has been now done over and over and over again. And so, there has to be some truth to it. And there's many testimonies. And again, we just have to hope that the anecdote becomes data points. And those data points become, a study, become an experiment, become a scientific conclusion. And so that's why I think we're still struggling with. And again, if you don't let people do things, meaning that you cannot register your trials or they have to be done abroad and some other conditions, then it's just slowing everything down. So the science suffers too, right? Because you want to know ABC, but you're not allowed to ask ABC. Not here, but somewhere else you can. And so I think that's not a good environment.
Definitely. And it's funny, I'll mention that Roger Ver spends most of his time in Tokyo, Japan, where he's the CEO, or he was the CEO, and now he's the chairman of Bitcoin.com. But he lives in St. Kitts, which is also in the Caribbean. So he actually ended up flying to Panama, to have this done. And he didn't, do the stem cell injections in Tokyo or Japan. So while I hear you on Japan, I personally haven't heard a lot. It could be language barrier, culture barrier, but I've heard a lot of things happening in the places that I've mentioned for stem cell injections. So moving on, we need to wrap this up soon, but there's a couple major things that I think we should end on. So we've talked about gene therapy. We've talked about George Church. I've interviewed Liz Parrish, and I'd call her a friend. She's a phenomenal person. There is controversy around what she's done, but in 2015 she was the first person to have known publicly to have a telomerase gene therapy, and this has been controversial and still is. Since then, there's been more people to have telomerase gene therapy. On that same day, and by the way, she went just outside of Bogota, Colombia to do this because it is not legal in the FDA to have telomerase gene therapy. And so she's an American. She lives in Bainbridge Island, just outside of Seattle, Washington. And, she also had a myostatin inhibitor gene therapy. It's follistatin is the same thing. It inhibits follistatin. So which helps build muscle mass and prevent sarcopenia. For those who aren't aware, sarcopenia is, a disease of older people who have their muscles just wasted away and they're so frail. and you fall and break your hip when you have sarcopenia, and then you're near death, and then you end up dying of like pneumonia or something. And they write, what's the cause of death? Pneumonia. Well, it's not that simple. You died because of myostatin inhibitor. You didn't have enough follistatin. You lost your muscle mass. You got sarcopenia. You fell. So this is why aging is so complex and so multifaceted, and why this will lead to my final question about what can we do and what do you think we can do to solve this problem. But what I'm getting at right now with the gene therapy, Leo, I'm building here. What do you know like about telomerase gene therapy, and what do you think about like gene therapies in general? Because George Church thinks that maybe we can start actually really solving the aging problem around 2030 for humans for gene therapy. I mean, do you follow this much, or did you know about Liz Parrish and this story? What are your thoughts on this?
Yes, so I know about gene therapy. I know about Liz Parrish and about George Church's, or at least some of his ideas. So I should say, gene therapy has a very interesting history. Like first in the 90s was when people were like going at it. Well, the idea is from the 50s or the 60s, which is basically you have a metabolic disease where a certain enzyme is not made. So what do? You just put that enzyme in there, and so you fix the disease. Like also like lysosomal storage diseases, which I think are more prevalent in the Jewish population. They lack an enzyme. So you could imagine just putting that gene in, and now you make the enzyme. So this is ideas from the 50s or the 60s. But then it was in the 90s that you have the retroviral vectors, so vectors to deliver DNA derived from viruses. And you did a lot of it was actually in HSCs, in the blood stem cells. Because again, the blood stem cell, it can divide forever, and it can give rise to all your cell types in your blood. So it makes sense to use that kind of mother cell of the blood. And so, a lot of successes, but unfortunately, also some deaths. And that was because the way you put the DNA in, at that time at least, was as important as what gene you put in. And so if you do a retroviral approach, or viral in general, that is integrating in the genome and use many copies, that piece of DNA is going to land somewhere random in your genome. And so if you have the bad fortune of that piece of DNA landing in a gene in your body, in your DNA that controls, cell cycle, cell proliferation, basically cancer genes, you could get the cancer. And so a couple of people died from leukemia after it was genetically modified in a way that one of their cancer genes was interrupted, it was dysregulated, was destroyed by this insertion. And so then it was like kind of and then it went down a little bit, the enthusiasm, but now it's gone back up, and with reason, because now we have better technology. Again, it's a matter of technology. Okay, so the DNA was not inserted in the best possible way. Can we improve how we deliver DNA to cells? And so that's CRISPR-Cas9, because now we can make precise deletions, we can make precise insertions, such that instead of inserting 10 copies randomly in your DNA, you can put just 1 or 2, and you know exactly where they went and how many they are. And so that's a new wave of cell-based gene therapy. And so many of these are immune diseases, like and also blood disease, like anemia, for example, like falciform anemia, sickle cell disease, SCD. You could fix it. It's a molecularly defined disease. The first one to be so, actually. It's a single amino acid change in the hemoglobin protein that makes your red blood cells become sickle-shaped. That's why sickle cell disease. And so you could fix that disease by taking the person's HSCs, correcting the hemoglobin gene with CRISPR, and then putting those HSCs back in. And now these newly HSCs will make will make red blood cells with good hemoglobin. So that's one very straightforward example. And so you can expand that for other examples. And so that's where gene therapy is right now, actually, because only recently was there a study with the CAR T cells I mentioned for cancer, that on top of the chimeric antigen receptor, this artificial immune thing, you can also have CRISPR to delete a certain gene. So when T cells go into tumors, they become exhausted, they become tired because of signals that the tumors have. So you can use genome editing to make the T cells deaf to those signals. So you're going to delete this receptor on the surface of the cell, that usually makes it become exhausted. And so you now have this combined CRISPR-CAR T cell therapy that is now shown that is safe in patients. It was actually done in China, it's not even in the US. I think they might be a bit ahead of us, unfortunately, or maybe science is science. But so you have that. And so that's where gene therapy is. I mean, there's been an idea of like, okay, can we now restart the clinical trials for gene therapy with this new, safer, cheaper, more precise CRISPR technology. And then, of course, this is in the clinical trial setting. Now, what that means that now people can also start playing with it because it's so cheap and so easy. I mean, the CRISPR-Cas9, so the Cas9 is an enzyme, endonuclease, so it cuts DNA, and you can tell it where to cut by having a guide RNA. This is an RNA molecule, like very short, that will bind exactly in the DNA where you want, and then it goes and it cuts there, the Cas9. And so I know a friend of mine, Josiah Zahner, is a biohacker. He's here in the Bay Area, and so he actually sells CRISPR kits. I teach in South America, in Bolivia, every year, and it's called Science Clubs Bolivia. We started back in 2016, a bunch of us back at Harvard, and actually I use these kits for teaching. Because you have the bacteria, you have the guide RNA, you have the Cas9, even gives you the pipettes and the petri dishes to grow the bacteria. And so what this means, the bigger picture, though, is that it makes this type of science more accessible to people. And I think that knowledge is power. And so, so that knowledge can people do something more. And so now I see people that also do gene therapy. And so I think what Liz Parrish did was like, well, I want to modify this specific gene, telomerase. So there's a very interesting gene, right? I mean, back when we were still learning how DNA gets replicated, there was this problem, which is we have the leading strand and the lagging strand when you open DNA, double helix. And so how is it that, at some point it has to end? And so actually over time, our chromosomes get shorter and shorter, except in cells that express telomerase, because this enzyme will elongate your chromosomes, the ends of your chromosomes. It brings in its own RNA primer, and so it can do it that way. So now it could be, so that's where it gets complicated, because telomerase is found in two types of cells. It's found in stem cells, and it's found in cancer cells. So you want your stem cells to have plenty of telomerase, so they stay immortal. But what you don't want is a cell getting telomerase and then becoming a cancerous cell. Now, what's the risk? Now, does telomerase increase the risk of cancer? I'm not sure. Because just because a cell divides for longer does not mean it will become a cancer. It just means it has more chances of getting a mutation that will cause cancer, right? Because cancer, at least the current model, is a multi-hit genetic disease. And so the more times the cell divides, the more likely it is to get that one mutation or two mutations that will make it become cancerous. But it does not affect for example, your immune system, right? Every day we have probably millions of cells trying to become cancerous, but they can't do it because as soon as there's a mutant protein, that HLA, right, shows that peptide that is mutated, and a T cell goes, a T cell comes and kills it. And so our immune system is called immune surveillance, right? So the immune surveillance keeps most cancers at bay. That's why most people don't have cancer. Otherwise, we will have cancer because they have 40 trillion cells, as I mentioned. So it's a very high chance that of 40 trillion cells, if you account for DNA repair mechanisms failing, it will be more likely than what it actually is to get cancer. But thanks to the immune system, that doesn't happen. So now I guess, I don't know if it's not up to me to decide if it's right or wrong to do it or what the risks are, but I think these things, however, there could be some benefit to them, which is we need to learn more different ways to do gene therapy. Again, the CRISPR is a great advance because it's just more precise. There's less off-target effects, meaning that you're not cutting what you don't want to cut. You want to target this gene, not something else. And so that's been a great gain there. And so, like George Church himself has a list of genes to change. He's like, okay, these genes are, you could imagine this project where you sequence people who are 120 years old and people from families that they die younger, maybe, I don't know, for some reason, and so you could sequence those and then compare them and see, okay, what do these super centenarians have that normal people don't have, or that people die young definitely don't have? And so you can have a list of genes to either get rid of or down-modulate, also either get rid of or improve. And so I see potential there. And so I think a lot of longevity companies actually are doing this in dogs, doing in pets first. Like you want your pet to live 30 years instead of 15, then you could try this. So I think that that's actually a very interesting mechanism that we would hope that, dogs are, a good, if nothing else, there will be a good system to try these things where, okay, what if I go to this list of genes, if I modify them in my pet, is he or she going to live longer? I think that for me, that's an interesting way to go about it.
Definitely. And I'm friends with Dr. Bill Andrews, who a lot of people don't know, but he's the one who gave Liz Parrish at his office, Sierra Sciences, the telomerase gene therapy and the myostatin inhibitor gene therapy in a small dose, which she had to then scale up. And Dr. Bill Andrews, I've become friends with him. He has his dog, who's a similar type breed to my dog, and he's very interested in extending pets, cats and dogs' lifespan through telomerase, lengthening their telomeres. So, and Bill Andrews is also involved. He's the co-founder of a separate company called Libella Gene Therapeutics, where they have aspirations to do telomerase gene therapy on humans as well, but they can't do it in the U.S. because of the FDA. And I've also interviewed Dr. Michael Fossel, who is a PhD and MD, both from Stanford, a very incredible person. He wrote the book Reversing Human Aging in 1996. And if you go back and read that book, it's actually still pretty incredible. That's one of the most incredible and frustrating things for me personally. Just during this conversation, Leo, you've talked about, gene therapy. They were talking about that in the 50s or 60s. That's my worry. That's my worry that we're going to, that my son is going to be interviewing some brilliant stem cell biologist, maybe 30 years from now. And they'll be like, we've been talking about this for years. We haven't done anything. That's what we can't let happen, right? That's why I'm so passionate about we have to do things, right? We have to take in certain risks. I feel like we're just too risk adverse in this because I almost, from interviewing people too, I feel like it's not one individual who's risk adverse. I talk to reasonable people like yourself. You're like, yeah, sure, we should do this, we should do that. But I think it's the system which is stopping people from scientific advancement. So we have to find ways to get through that. But so yeah, with regard to Liz Parrish and things, I agree with pretty much everything you said there. We'll see if she how she looks and feels in her biomarkers over the next 5-10 years. So um, we'll keep you in touch with what she's doing. So the final thing, Leo, you've been really gracious with your time. This has been a really long interview, but it's been awesome. The final thing is, my question for you is, and I'm going to start asking people this question because I've been thinking a lot about it. Let's say you have basically infinite resources, right? Let's say that you're a trillionaire. What would you be doing right now to slow, stop, and reverse your own aging as a biohacker on yourself if you just had infinite resources? And take as long as you want, and think about it. What would you be doing? What would you be trying on yourself?
Very good question. I think I will still be targeting the insulin pathway axis because that's really what's been shown among different species, right? So you have the C. elegans worm, Drosophila fruit fly, we have the Mus musculus mouse, and even in humans there's some evidence. And so now the next question is how to really get control of it, because it's you can change the way you eat or how often you eat, but in the end it's going to boil down to something, right? Something molecular, something cellular. And so that's really something to look into. And so I think I'll definitely bank my HSCs. This is well known that, with aging, HSCs, they change their behavior and what cells they can become. And obviously it also accumulates DNA damage. I mean, that's all our cells are constantly accumulating DNA damage. That's just physics, right? It's UV radiation, it's toxins that we ingest. And but that's more of, I think, as I mentioned at the very beginning, the insurance policy. That's a preventative. And then for myself, I think that'll really be the one thing. And now, I guess, would there be a way to find a molecule? For example, there's these really cool experiments with parabiosis, where we stitch together by the circulatory system, that is, of the young mouse and the old mouse. And if you look at the mice later, the old mouse becomes younger. The young mouse, I'm not sure, actually suffers anything from it. And so what that means is that there's something lacking. Well, it could be two things, right? It could be maybe the old mouse. Well, the old mouse is definitely lacking something. I think that's what it suggests, at least. And now the question is it an activator or is it an inhibitor, right? So maybe, either the old mouse has too much of something or too little of something, of some activity, right? And so there's actually some other work showing that, actually through blood, which is everywhere, and actually the blood could communicate your organism's age. So like if you have a brand new liver, but everything else is old, I think over time your liver might also become old and jaded. And so I think that's because, everything communicates with one another. And so if we could change that, so like, blood is life, and it could also be youth. And so if only, so maybe I'll dedicate myself to that, because blood we can manipulate. And of course, I wouldn't want the whole blood. I want just the active ingredients of the blood that do it. So there's a few candidates. One of them was called GDF11. He's actually worked on at Harvard, like Amy Wagers, and then partnered up with Lee Rubin and Richard Lee. And so the effect is there. Many people also at Stanford, like Tom Rando, I think there's some small trial where they're transfusing blood from a young people to old people. So this is real. This is happening right now. And so we know there's something there. But so I would really put my fortune and my type and my time towards really finding that. Because then once we find that and we can produce it, that will be a game changer. Because if you can, if nothing else, maybe a lot of it, it's not psychological because it's this body, but what if it's just a lot, it's just like your body thinks it's old. If you trick your body to think it's young again, then will it change? Because, we have unlimited food and, we have unlimited nutrients, right? So there's no lack of nutrients. So then there's no really, like, you could say, well, if you're starving, then you can't really do anything about it. But if you have food and comfort, there's no limit to like how much you could keep convincing your body it's still young, because you're giving it enough nutrients, you're giving it all the good stuff, and you yourself having a good life. Nothing has changed. Like if you play, let's say, the same number of hours of dodgeball every week, and you eat the same thing every week, like how does your body know this week from the next week, from 10 weeks ago, from 20 years ago? Right? Because there's accumulated damage. But like, can we reverse that damage? At the cellular level? Because again, if you have adult stem cells, if your cells are damaged, well, just replace them. And so, there's two ways. So one would be to like replace them from the outside, or make your endogenous cells somehow become rejuvenated. Actually, on this note, so the salamander, the axolotl, Mexican salamander, more precisely, one of the reasons why it seems to be able to, like, if you chop its arm, it grows again, and if you take part of its brain, it grows again, is because it's retained in this immature state. Like the gills are still outside, and there's all sorts of like infantile traits in these animals, even in the adult life. And so can we somehow, not mentally stay infantile, but our body somehow, if, like once you're a young adult, if we developed, like you're, but then once you pass your 20s, that's it, right? You don't need any more like adulthood, if you will, in your body, physically speaking, right? And so if there was a way to keep your body in that state, like I don't know if there's some fact in blood, because then the blood communicates with your whole body. Something about the brain too. In the neurons in the brain control your appetite, like, your sense of balance, like a lot of stuff is in your brain, obviously, or perhaps not as obviously, but, and actually, also interesting, I'll also invest in, I guess, right, my project number 5, but there seems to be some connection between the nervous system and the immune system. Crazy stuff. There's this, I think his name is Kevin Stacy. He's in New York, and he found this thing where you infect mice with bacteria, actually LPS, lipopolysaccharide. Is just, it just looks like bacteria. It's what bacteria have that make you very sick. So sick you can die if you get into septic shock. And so if he has a control mice, they just drop dead. But if he cuts out the vagus nerve and then infects the mice, they stay alive. So it's as if the brain didn't know you got an infection, then you're fine. But if you do, you die. And so what is it that connects the nervous system to the immune system? Now, there's some clues since that experiment. It turns out that immune T cells express cholinergic receptors, and they make acetylcholines, like stuff they usually think are neurotransmitters. And so T cells, immune cells, can make them too. And so, yeah, there's some obscure. So two things I was focused on. One is the blood, and the other one is the nervous system. It connects to the immune system. So if you could control these two things, it's a bit like, the stuff about hypnosis. You can make someone go back to their previous lives. You can get someone feel healthier. Maybe it's not so crazy after all. We just don't understand how it works. And so that's the kind of stuff I think I would invest time and money in.
Wow. A lot of really fascinating ideas there. And I really agree with what you stated there. And on my YouTube channel, you can check back in October, also at RadFest, I interviewed Dr. Dipnarine Maharaj, who is running the largest clinical trial on young human plasma transfusions. So what that means is he's been taking young plasma from 16 to 25-year-olds and injecting it in people who I believe are over the age of 55, I believe was the lowest age. And I think they cut it off at 91 or 92 years old. Whatever it was, I joked. I was like, oh, what about the 93-year-olds? You know, man, why are you hating on them? But I need to get in touch with Dr. Maharaj again. We were on video conference a few months ago, but I need to check in and see how that trial is doing. They needed $10 million and they didn't have it all yet. They needed the full $10 million to do the full clinical trial. But I think that there's a lot of interesting things that we can learn from there. I will say that I've had phone conversations with Dr. Jesse Karmazin. He is a graduate medical doctor of Stanford, and he is the founder of Ambrosia, and he's since rebranded the company to IV Plasma. I think the FDA, he had issues with the FDA last year in 2019, and I think he shut down Ambrosia. But they basically look like they're doing the same thing at IV Plasma. There's a lot of controversy with it, but essentially he's doing the same thing. He's charging $8,000 rather than doing it for free, which is what Dr. Maharaj is doing. He's charging $8,000 for people to do young human plasma transfusions. And then at IV Plasma, they now have a $4,000 option, at least last time I checked, for just half the dosage. And I've talked to people. I've talked to Jesse Karmazin himself. He said he's injected himself with the young human plasma. He's about my age. I think he's about 35, maybe 36 right now in 2020. And he said anecdotally that he thought that it improved his health. And they did 5 biomarker tests. And at the time in late 2017, when I talked to Jesse on the phone, he said that the 80 people that he had done the young human plasma transfusions to into the old people, all of them had all 5 biomarkers that they tested showed reversal of aging. So, I mean, it's pretty exciting. He did it on his dad, he did it on himself, and anecdotally he said, hey, I live on the 5th floor of an apartment complex in Tampa Bay, Florida. And I would take the stairs, trying to get more exercise. And by the time I get up to the top floor, I'd just be like exhausted. After I had the young plasma transfusion injection, like all of a sudden I walked up 5 flights of stairs and I realized I wasn't exhausted. So those are the little types of, it's just an anecdote, but it is important. And I talked to other people at RadFest who had the Ambrosia young plasma transfusions, and they've just raved about it. Meanwhile, you Google it and you read in the mainstream media, you read articles and you listen to people, these credible scientists, and they say, this is horrible. What are people doing? This isn't proven. And this is dangerous. And like, what are you talking about? First of all, this is plasma. We've been doing plasma transfusions for decades. I donated plasma when I was in college just to get money, for people. Right? Yeah, I did it for beer money. It was like 25, 30 bucks and inflation adjusted money in 2003 in Kentucky. That was a lot of money for me to get 25, 30 bucks back then in 2003. So first of all, I don't see really the risk factor in it. Again, I go back to, are there risks? Sure, there's risk for everything. Walk outside, we're driving the car, there's risk. The question is, are we managing risk intelligently? And if this is done properly under the guise of like a medical doctor, Stanford graduate like Jesse, who, by the way, the parabiosis that you mentioned, a lot of that research was done at Stanford, and Jesse was at Stanford, doing that research. So this is what seeded him with this idea to do this and found this company. But it's just been incredibly difficult for him to the point where he doesn't even want to do an interview with me because he doesn't want, for whatever reason, doesn't want certain information to be out there because of what he's worried about the FDA breathing down his neck, essentially. So I just hope that I'll get back in touch with Dr. Maharaj and see, where that is. But I'm very excited about young plasma transfusions because of the things that you talked about. And there's thousands of proteins in the blood and in the plasma, and we believe that those are having an effect on health. The younger ones, they know that you just mentioned GDF11, right? We know that there's more of that prevalent in younger people and less of it when you get older, and vice versa with all sorts of things. We know there's more certain proteins as you're older and less of certain ones as you're older. So we just need to do more research on this stuff. Alkahest is another company. They're in San Carlos, California, where I used to live in the San Francisco Bay Area. They're doing research on this. They're only doing it on mice. They're the ones that have been. I've seen a number of their scientists and their employees, quite frankly, just hating on Jesse and ambrosia and IV plasma. So I really want less of this. I want people to be more open-minded and to listen to people about where they're coming from. And I don't think we've had enough of that. Leo, I see all of that in you, right? That's why I've loved interviewing you. And I hope that the scientific community can just be a little bit kinder to each other too, because I feel like there's some mudslinging that's not necessary, and it seems like it's over like money and prestige and things like that a lot of the times, where it's like, hey, let's just solve this aging problem. Let's work together to help improve people's lives, because at the end of the day, that's what this is all about, and that's what this should be about. And I know that's what's driving you and motivating you. So I really appreciate you taking the time to share all of your experience, knowledge, with the audience here, and hopefully we can make this a reoccurrence where we can interview you and have you on every few months or something to share updates and network together, because that's, at the end of the day, is what's the most important thing, I think, networking, so that we can solve the aging problem. So Leo, final words for you, whatever you want to say or share or leave the audience with.
Well, I mean, thanks so much for the opportunity. I think we touch upon a lot of interesting subjects, and so I think in general this idea that, again, aging is a very important problem, and it is solvable. Like we have a lot of knowledge coming from biology, from biotechnology, that we can do many things today that are not being done because of non-scientific reasons. There's not enough funding, not enough people working on it, not enough interest. And so all these are very solvable. It's not rocket science. We know a lot about how to grow cells, how to purify the cells, how to modify the DNA, and with different models. And so this is all work just waiting to be done. Like imagine you're baking a cake and now you can't take it off the oven, but you have to, because otherwise, it's gonna be spoiled. And so I guess what I mean is that what you don't want is to lose a whole generation of people that could be working on this stuff, and they want. Because the grant doesn't stretch for long enough, or there's not enough lab space, there's not enough interest. I mean, I think there will be a big loss that is going to haunt us for many centuries, right? Because whatever, I think you said, the longevity escape velocity. If we don't hit it, the sooner we hit it, the better. And so every year that we do less research than you should, it's going to compound. Like Buffett, I guess, could talk about this better than me, but this loss in research years is going to compound and compound. So like 10 years from now, it's like, if we had done that 10 years ago, we would have the answer by now, because science takes so long. So every bifurcation you take, you got to be careful what decision you make, right? And so I think, again, we're losing not just those days, we're losing like years ahead, because we don't have that data, that knowledge in the future. And so I think for me, that's the main thing, like there's a lot of brilliant scientists working on it. There could be many more. There's a lot of technology that is ready to go. Right, we can grow cells in large quantities. We can change their DNA with precision. We have animal models. We have clinical trial structures in place. I mean, see with the pandemic, see how many trials have been started. See how many papers have been published. See how much money has been poured into it. So everything is in place. It just has to be used. And so it's clear not the job of one person or 10 people or even 1 million people. It has to be almost, like the whole world, or like entire countries will be coming together and be like, we're going to focus on this. We're going to work on this. Yeah. And the benefits are many. Even if you don't care directly about aging, that's okay. But think about all the other benefits that come from it. Just like from NASA, research at NASA, even if you personally have no interest in getting to the moon, credit cards came from NASA research. And so they affect you on Earth. Well, if you have faster cars, if you have better insulation in your buildings, it's because someone wants to insulate their rockets. And because they want to work on rocket insulation, now your house is better insulated. And so
MRI came from NASA as well.
Yeah. So all this stuff that affects you today or in short term, which can then compound to have effects in the long term. And so again, I think aging research, because it touches upon so many aspects of really fundamental biology, like why do we age? How do we age? How do different animals age differently? Like, what is it about the naked mole rat versus a normal mouse? I mean, they look almost the same. It's just one is maybe uglier than the other one. But they live, but one of them lives 10 times longer. Like, I think we can figure that out. Or like, even like, I think different types of reptiles. Like, one only grows the tail, the only grows back the tail and the arm. The other one does that plus part of the brain. I mean, again, comparative zoology, which is like a very old thing, like Linnaeus was working on this stuff, naming flowers and animals, with Latin names, but, 2020 is still relevant. Like, we should enjoy our biodiversity, and so we can learn from around us. I think so much of biology, a lot of it is creating, but so much more is just imitating. We're just imitating. Like, we do all this biomimetic stuff, like adhesive molecules that just imitate what the reptiles do when they climb the wall. So we just have to, nature already did a lot of experiments for us. Like when we have like mutations causing disease and then stuff happens, nature already did the experiment for us. We just have to look at it, to imitate it, to understand it. So again, this is really just like pressing and just waiting to be done. And it can be done today if we have to.
Beautifully stated, Leo. And with your analogy there of like baking the cake, which I've never heard that analogy, but talking about the people we talked about earlier about who like, don't think it's a good idea or don't want to solve aging, it's kind of like they're the ones saying like, don't take that cake out. We don't know what's going to happen if you take it out. It's like, yeah, but we know what's going to happen if you leave it in. That thing's just going to get burnt and it's going to be worthless. So at some point we got to try something, or we're all just going to end up dying of aging, right? So we got to try stuff to solve the aging problem. So I love that analogy that you used there. I've never heard it, but is that the first time you just think of that, or is that go-to for you?
I swear,
Yeah. Interesting. Okay, awesome. Well, Leo, it's been a lot of fun. I'm sure we could always talk about more things, so maybe we'll have you on again. But I really, really appreciate your time. And remember, if you haven't yet, definitely subscribe to our channel, subscribe to Leo's YouTube channel, link in the description below. Follow him on social media, Twitter, Instagram, Facebook, LinkedIn. And Leo, final word from you.
Well, thanks again for having me. Please keep fighting to inform people about aging and strategies to fight aging. And again, just so everyone knows, a lot of science fiction is no longer fiction, it's just science. And we have very powerful tools just waiting to be deployed to work on this very important problem.
Boom. All right. Thanks so much. And we'll see you all in the next video.